Everyone, good morning and welcome to day 2 of our conference. I hope you had a good time yesterday in Amsterdam and had a restful night. Same as yesterday, let me share a couple of organizational remarks. So all the coffee breaks and networking breaks will be held in front of the conference room. The toilets are located on the right, and for the lunch we will go to the restaurant, which is located across the hall on the left. Also today we have a site visit after lunch. For all of you joining the site visit, my colleague Teresa will send you an email very soon with a detailed schedule. Also, you can pick it up at the registration desk after lunch, and the meetup point is the lobby of the hotel. So if you have any questions in the meantime, you can come to me and we will solve it together. So the site visit is right after lunch. There is no need for any special equipment. It's inside, so the weather is not a problem as well. And we will meet each other in the lobby after. Also, I would like to thank, of course, our chairman, Jakub. Thank you very much for your guidance, and I will hand the mic to him in just a second. Firstly, I would like to thank our sponsors as well, Alcatel Submarine Network, Wirescan, and Waves Group. Thank you so much, everybody, for your support, and enjoy the second day.
Good morning. So there are a bit fewer people today than yesterday. So I'm still going to do the survey though of the energy level. What is it today on a scale of 5? Is it still 5? It's 6. 6. Okay. Yeah. Well, I don't see that many hands up. I'd take those as zeros. So we will need the coffee break soon. But let's get started anyway. I'll not drag this on so we can get moving with the agenda. Our first speaker will be Mike McLaughlin from ABL. There he is. I was worried. Didn't see you. Mike.
Yeah, good morning. Mike McLaughlin from AVL. I get the honour of speaking to you all after a nice house in Amsterdam. I hope you can keep awake. What I'm going to talk about this morning is a little bit about the role of marine warranty surveyor, which was mentioned yesterday by Matthew and Andrew. A little look at the new scope of work that the Joint National Natural Resource Committee issued earlier this year, and also share with you some of my thoughts and experience looking at HVDC cable protection and some of the issues that I see there. Found the right button. So I'll start with the role of the marine warranty surveyor. And the MWS, as was described yesterday, is a third-party independent body that's appointed by the developer as part of the marine the construction's all-risk policy. And we're engaged as a third party, almost due diligence process, I suppose you could call it, to look at the engineering and the methods and the equipment used for the installation of the assets during the construction phase, and we act as a sort of independent eyes and ears of the underwriters to ensure that risks is reduced to a minimum level. And how we do that is we review the starting off with the basis of design, then look at the installation methodology, installation engineering, review the risk assessments, take part in the HIRAs, we vet the vessels, we look at the equipment to make sure that they're suitable for the intended purposes, and then we go offshore, witness the preparations, and issue certificate of approval for the operations to commence. And this is really a flow chart of that process to show you that process. And the issue of the certificate of approval shows the underwriters that process has been undertaken and that operation should fall under the auspices of the construction all risk policy. And our scope of work is generally informed to us from the JNRC scope of work. A new one for renewables was issued earlier this year in March, and in that they've introduced a new section on interconnectors. As you can see, it covers all of the stages: the cable manufacture, load out, transportation, storage, which wasn't really in the previous version for subsea cables, cable landfall, cable lay, and cable protection activities. And in part of that news, and part of the scope of work 7 for interconnectors, they've introduced a requirement to look at the onshore cable as well as the offshore cable. We're looking at that at the moment to see how much we need to delve into the processes for the onshore cable installation. We at the moment we're viewing it as more of a due diligence look to make sure that the right processes are in place and the right permissions and the route is well planned, as opposed to looking at the actual the methods. But I'm sure that will come, and we're currently discussing with JNRC exactly how they see the role of the MWS in that, because it also includes the onshore substations, which isn't really a marine activity apart from the transportation of transformers and things like that. It also brings in the commissioning side as well. So again, we view that at the moment as just reporting back on progress to the underwriters more than anything, to make sure that they're properly informed. Includes the cable manufacturer, but it's again more of a due diligence to show the underwriters that the cable has been designed to the right standards and using the right processes. The cable has been undertaken a fat test, whether it's type tested, and all the things like SIGA recommendations are adhered to. Because I think it is recognised that the developer will have appointed their own cable experts to monitor the manufacture of the cable, and you can only have so many people standing around with a clipboard during the fat test and other manufacturing activities. And of course, it's also quite difficult at times, depending on the cable manufacturer, to actually get access to the cable factory to look at the cable being manufactured. The scope of work also gives a clear indication of the attendance requirements for the marine warranty surveyor. Things like export cables and interconnectors is generally 100% attendance. So we're there all the time offshore, the cable's being installed and buried. But when you look at array cables, which are a lot more repetitive operations, shorter, more repetitive operations, we generally only attend for about 20% of the time. And then witness, or well, not witness, but monitor the progress of the installation using the daily reports and progress meetings with the vessel. So I'll move on to some of the risks that I see, particularly with HVDC installation, in particular the fibre optic cable, which is generally part of the bundle of cables that's installed. And I've seen issues with, first of all, cable design, the bundle integrity, which then leads on to issues, or can lead on to issues with burial and protection. We look at the cable design. We have seen some HVDC cables where the fibre optic cores, or there are fibre optic cores embedded within the armour layer, which can, we have seen a number of failures during installation because of that. Because if you consider the amount of protection given to the fibre optic cable in a HVAC cable, where the fibre optic is embedded within the packing and underneath the armour layer, to have some of the fibres within the armour layer does expose them to the risk of damage, particularly at bend radius or particularly during transit through depressors in burial tools. And cable in the bundle can give issues, particularly if the bundling, when the cables are laid from the vessel, you've got three cables going into one bundle, generally through a bundling machine which wraps them all together. And if that bundling becomes loose or broken, then that can cause issues with the particularly the fibre optic. If in the catenary from the vessel the bundle is loose, then one cable might be taking more stress and strain than the other, for example. And if the fibre optic is a bit slacker because you maybe haven't quite got the tension is synchronized, so you're feeding one cable in more than the other, the fibre optic cable can tend to sort of pop out between bundles, particularly if the cable is in a catenary, and also if the bundling is loose, there is a risk when the cable goes through the ploughshare or the trencher depressor that the fibre optic can fall between the two, the bipole and the dipole, and become crushed. And quite often the fibre optic cable may have a lower crush limit than the HVDC cables themselves. With shallow water insulation using a burial tool such as a vertical injector, those cables aren't bundled together generally because it's not possible to fit a bundling machine within that within the setup to feed the three cables into the vertical injector. So there's a greater risk of fibre optic cable damage because the cables are not bundled together, and the fibre optic cable is more at risk. Again, if you're post-lay burying with a trencher, if the bundling becomes loose, then the cables can separate, which make burial with the trencher very difficult because you need to get if it's a jet trencher, for example, you need to get the bundled cable contained within the jet trenching arms. Or if it's a cutter, again, the cable needs to go into the bell mouth of the or be fed into the cutting trencher. We've also seen damage, particularly in ploughs or vertical injectors or cutting machines, where cobbles have been ingested into the cutter or into the share or bell mouth, and that has caused damage as well. So when we look at HVDC cable lay, we do pay particular attention to ensuring that the speed of feeding the cable into the bundling machine is well controlled and synchronized by monitoring the length and the payout speed and setting or ensuring there are critical speeds and synchronization set. We look at ensuring that the bundling is good. The bundling is as tight as it can be, and if possible, have a dual system so that there's two separate layers of bundle or additional straps applied. Monitoring the cable as it's being installed is essential to make sure that the bundle doesn't become separated or the cable separated on the seabed. Monitoring the trencher load cell to ensure that the lowest crush pressure of any of the cables isn't exceeded, and for the fiber optic cable, the use of double armor as well, if necessary. And that's all I have. Thank you very much. If anybody's got any questions.
Thank you. So, do we have questions in the audience? We have one. Yeah.
Morning. Thanks, Mike. Given that one manufacturer has laid over 1 million kilometers of fiber optic cable to date, and if you put all of them together, we're probably well beyond 2 million around the world. I think it's inferred from what you've said, but just to draw it out, what is, in your opinion and experience, the key factor why fiber optics more vulnerable in this scenario and this industry when it isn't in its own industry?
I think the greater risk here is the fact that it's not a single cable that you're laying. It's the complexities of making sure that the fiber optic isn't damaged either by the burial system or damaged by the other cables within that burial system. Because you're adding an extra pinch points.
So I sort of I think it's the vulnerabilities of not looking at. Everybody's focused on the power cable, and not looking at the other parts of it, and its tool equipment selection.
Yeah.
And looking at because normally the fiber cable is more resilient than a size for a power cable, certainly.
Generally, I mean, generally, depending on where they're being laid and the risks, of telecoms fiber optic cable nearer to shore will have double armor. Some of the cables we've seen for HVDC have only been single armor.
Yeah.
And the fact that they're interacting with other cables at the same time doesn't help. And we've seen people expecting, for example, cable bundle goes over the chute nicely like that, but by the time it gets down to the bell mouth of the trencher or the plough, which generally can be not a square or a circle. If the cable twists, for example, then that can cause additional problems as well, particularly if the bundling has then become loose or slackened off a bit.
Thanks.
It's not an exact science, that's for sure.
Definitely not. Thank you.
We have a question in the back.
Hi, Chris and Mike. Nice to see you both.
What is this, ganging up on me?
No, I'm going to do the opposite. I've actually got a slide on that a bit later, so we can talk about the types of fiber optic cables that are being used embedded in the package. So maybe we can draw on that a little bit later. So ask the same question again a bit later, Chris, and we'll see if we can explain it.
See if we can get a different answer.
Good. Then a question from my side is, we saw you mentioned fiber optics being integrated into the armoring layer, and that causing challenges. I understand if that shows up when you're looking at it, it's already 2 years too late to change this, right? Because it's cable design choices.
Yeah.
What's the way to feed that back and make sure those challenges don't arise again? And how did we not avoid them in the first place?
I think the cable design is a totally different sphere. The company that designed that cables is now aware that there are issues with putting the fiber optics within the armor. Whether they do that in future designs, I don't know if they will or not, because they then have to go and repair it, and it affects their warranty of the cable for sure.
But that is a challenge you see with those designs, or is there something that during installation went different than expected, and then there are problems?
Well, I think part of the issue is, I suppose, call it an issue. Is it an issue? I don't know. But each cable designer will have their own method and their own way of designing cables, and it's all very much protected intellectual property. And I don't think they share. There's a method of sharing experience or sharing lessons learned, which would be helpful if people did that, I think.
Okay, good. Do we have any other questions? Yes.
Yeah, Mike, just a quick question. What are those fibers normally used for on the bundle? Are they just for communications, or is it just for monitoring the cable?
Bit of both. For a wind farm export cable, for example, it's big used for monitoring the cable, but also part of the SCADA system to control the turbines. For an interconnector, it's probably more used for monitoring, I think, but don't quote me on that.
Good. Any final question? No, we're all satisfied. Good. But then, Mike, thank you. Good. Then our next presenter will be Henrik Bang Andreasen from Portnes Solutions. Henrik.
Yes, good morning. So, why can't the CPS protect the cables, or can it? So, that's what I'm gonna talk a little bit about. And last year, Renee was giving me a question about the CPS systems, and I had a short answer, and you and many others weren't quite satisfied with my possibly not very kind answer to that. So here's a more deliberate answer to that. I've had a cable protection company before that I sold to Balmoral in 2018. There's a picture from it up on the left-hand side, and now I do something different but I have a little bit of knowledge on cable protection systems that hopefully I can share with you today. So what we want to prevent, and now Michael, that probably is still taking some of his beauty nap this morning, told us yesterday that maybe we're having 1,500 or 1,600 failures in a 10-year period. I'm using his old data here that says 2,200 failures in a 10-year period in the offshore wind projected. That may be more. Some of the projects that I've been in, that's not part of this yet. In, for example, a wind park that's been inaugurated last year, where they have to change all the cable. That's not part of this statistics yet. So we will have a lot of failures. That wasn't the cables that failed. That's because of the CPS failed, that they have to change all the cables. So Jakob and Prisman can relax. It's not always the cables that fails. That's the reason why you have to change all the cables. But the consequences are, of course, very expensive and not good for the industry. And now it was said before that people can talk, and everybody wants to know when other people's fail, but nobody wants to share their failures. I think everybody knows this, and so this is the different thing. One of the reasons why does these problems remain unsolved, and this is kind of the thing that we can't think. But last year, the Carbon Trust came out with this cable protection systems best practice guideline, and I think that's a very good example of this, because here a number of the companies, they got the logo on. You can see there on the right-hand side, and I say principally the reason why the problem remains unsolved is because the forces, they basically are much greater than the design premises. And Band-Aid solutions exist. That's not me saying that they're Band-Aid. That's Ørsted that call the rock berms for Band-Aid. And the CPS best practice does not fully consider that the cable systems to rock berm interfaces, they prevent the soil spring from supporting the cable bend radiuses. That's very important. Why this is important, I'm going to tell about. And the cable to CPS interface inside the CPSs, this tube-in-tube that's supposed to be there, that the cable can freely move inside the CPS. This does not exist other places than inside the head of the analysis people and inside the head of the Carbon Trust people. Because we know, and this we knew in a specific project in Hornsea 1, we had to change 27 of the cables within 3 weeks after it was installed, because JDR had a small argument with Ørsted, and we had to change 27 of the cables within 3 weeks after we installed them. Then we found out that all the CPSs was blocked up with sediments. So this thing that the CPSs gets fully sedimented is not an end of life thing. It's a start of life thing. So what we do in the analysis, when the analysis people, they say that we have a tube-in-tube and the cable can move freely inside these CPS, is something that happens in the analysis. In reality, the CPS prevent the cable from moving inside the CPS. So when the analyst people come and tell you that these cables work fine in 30 and 40 years, that works absolutely perfect, but as long as it's inside the computer. So for all of you who wants to run your wind farm in a computer, that's fine. For those of you who want your cable in the ocean, in reality, you have a different animal to deal with. This, you know, from Deltares yesterday. And the thing, who owns the challenge? And here, the CPS systems and the CPS manufacturers have been a bit unfortunate. And the history from London Array and with Tecma being specifically unfortunate with their hypermobility systems that start rolling, where they put wheels to motion on the scar protection systems, of course, gave this industry a very unfortunate history, where in 2020, 2021, we actually found out that the cable protection systems were a big issue. And Ørsted had this campaign where they had started putting rocks on top of the cable protection system to stabilize them. This was good. And why was it so? I believe this thing with the silo thinking, where on the two left-hand side here, you can see that the thing around the CPS, where the issue where the CPS is basically found up around the mid-ocean data, around the seabed, the scar protection, and the foundation, where the contractor basically interfaces with the CPS manufacturer, where the electrical system around the cable and getting down to a cable data sheet is something that is two different worlds. And then on the right-hand side, you have three different things happening, where the CPS is looking into getting down to getting a local and global analysis made up, where the cable is being made in a separate thing, and the contractor is basically focusing in their own way in getting an installation analysis and a scar protection in place in three different silos. They should be interacting, and they are in some way, but it's very much three different, excuse me, three different silos. And they are there to solve which challenge. And you say, well, this is the same challenge, but if you look at the contractor's perspective and the operator's perspective, well, they're there to build the same wind park, but the contractor's perspective is focusing on the warranty period, and the operator's perspective is very much focusing at the operational period. They are, of course, both focusing on where the customer is the king. So both is looking at comply with the employer's requirement. But bear in mind, what I have learned in all the projects that I've been in, it's the customer is king, and the CPS systems are built to be installed. So if a CPS system can be installed, that's a 99% home run. If it then can fulfill, or if it fulfills the global and local analysis, it's a good system. This is basically the background for this. Back to the best practice. Now, if this system, this is a picture from the from this best practice that came out in November last year. Now, if you look at this picture, if it was so that this CPS system was filled with water around the cable, and if it was so that the soil spring system leading into this in the rock berm actually did provide a soil spring that would protect the cable bend stiffener. Now I really get away here. Would actually support the cable bend radius leading into the rock berm here. This would be a really good thing where you could actually put a lot of weight on top, a lot of ballast on top of the CPS system so it got stabilized here. This would be a good system. So why is this not a good system? It's not a good system because if the CPS system is filled up with sediments and we put a lot of weight on top of this, and we have a system, now they made this drawing to make it look like there's hardly any distance between the foundation and the rock berm. And therefore, there would be no movement between the foundation and the rock berm. And we cannot actually install a system where we have like 50 millimeters between the foundation and the rock berm. This is simply impossible. Or, of course, if you want to put out, 6,000 tons of rock, then we could probably do it, and our CPS system would be flat as a pancake. What we came from before 2020 is what you see on the left-hand side. Then we started putting on the rock berms as we used to do around the OSSs, as you see on the right-hand side. Which worked on the OSSs, where we couldn't get the trencher. We didn't have the space to get the trenchers in the cable around the OSSs. So the industry solution was that we start using rock berms. Now, for those of you who have not seen the armor sizes of these systems and think this is tennis balls size and it's nice and rounded rocks, I put a picture in of the armor rocks with me next to it. The grading is 60 to 300 kilos, and the shape you see here, this is armor rocks. So there's a number of issues with these, and these do not actually support, as I told you, these things. Why is this a problem? Gentlemen and ladies in the room, when you put something like this over a cable, and the cable is inside a CPS system that's partly or maybe even fully sedimented, you actually block something that's very critical for a cable. When is a cable flexible? It's flexible when the components of the cable can actually move. You need something which is called conductor slippets. It's very critical for the cable because if the cable is prevented from these slippets, the cable will damage if you try to flex the cable, if you try to bend the cable. The cable will bend between the aperture of the foundation. Doesn't matter if this is a monopile or a jacket. And it will bend in the movement from the waves down at the seabed. We have these movements, and therefore in the interface leading into the rock berm, you will have these problems. You will damage your cable. So why is it that everywhere else this is not allowed, but it is in a rock berm? We accept this. We build these cables, but we're absolutely happy to do this in a rock berm. Because there are contractors, they say, no, the CPS system shall just be strong enough to prevent this. And the CPS suppliers say, of course, the CPS is okay to do this. Because the CPS supplier have never told that they will accept the contractor to fill up the CPS with sediments. Because the Carbon Trust actually even mandate those that makes the analysis that it shall be water filled so the cable can freely move inside the CPS. So they're all free. Nobody does anything wrong here. There are a few other issues. We use articulated pipes. It's good to use articulated pipes as long as you make sure it's in the seabed, it never moves. So ensure it doesn't. There's lots of examples where people put the articulated pipes in places where it will move. And make sure it doesn't. Because people tell us it's corrosion free, it's abrasion resistant, and many other things. It's not. If you have articulated pipes in the water column or where it moves, it will last approximately 5 years. So if you have it other places, you have a 5-year approximately in the water column. VIV, it was mentioned yesterday. Here in the Taiwan Strait, we don't see this particularly in the European waters, but in Taiwan, you see this in Taiwan Strait, you see this. Here, VIV may be a problem as long as it's touching the seabed, and so we don't see VIV. As long as we have a very strong bend, we typically don't see VIV. So I was just going to talk a little bit about what we are doing. We're doing the autonomous stabilization system where we actually stabilize without putting weight on the ballast on the CPS systems. Very short, so we actually put down a bend stiffener on the touchdown point of the cable protection system, and we stabilize with screw piles through the scar protection. And that works fine without we get the pinning without getting compression on the CPS system. We can do this and we can save a lot of time on the installation, because when the rock dumping is done after the cables have been installed, the rock dumping, as you can see on the left-hand side over on the two graphs there, you cannot dump rock very efficiently on top of the cables. The rock dumping of the armor rocks, which is about 2/5 of the quantity of rocks, take 225% of the time as the filter rock takes. So if you could dump the rock before you actually dump the, or before you start your cable campaign, you could have installed the armor rocks in less than half time of the filter rock. So you could save a lot of time in the installation. And you would save a lot of time, not in the cable installation, but you would save a lot of time in the armor installation and in the so it's not really concerning the cable installation, but you save a lot of time in the total installation of the foundation and scar protection. And with something when you then get a bend stiffener at the seabed interface, where the CPS systems typically have a very poor performance, because you cannot have a strong bend stiffener at the seabed interface, because then you cannot install your CPS. You will actually have a very nice bending stiffener curve at the touchdown point. So that's one thing. The second thing is that we can actually provide a system that also provides a very nice free span capacity, so you don't have to do airbagging, or we can live with a free span in landfall systems. So that was very much what I wanted to say.
Okay. Do we have questions from the audience? Yes, we have 2 questions there.
Hi, Henrik. Richard Hill, Waves Group. Really nice presentation and great to see pinning back as a way of stabilizing. I've used it myself as well. A really good technique. You talk about the bend stiffener allowing free span capacity. So are you doing now a local analysis with that? Is the bend stiffener taking the load, or is it a global analysis of 2 separate tubes still, or is it actually coming together as a combination structure?
So you're asking about the global analysis, because we will have to do two typically depends if this is a retrofit or if this is a greenfield. So we will typically have to do 2 global analyses. if it's a green, if it's a brownfield, if it's a retrofit. If it's a greenfield, we will typically try to do a global analysis with the CPS supplier.
So you're now analyzing the bend stiffener and the cable together.
No, we'll actually do with the cable, with the CPS system and our bend stiffener together, because you now have two bend stiffening devices. You both have the CPS system and the bend stiffener in our PSS. So you effectively have two bend stiffening devices. There's a bend stiffening device in the CPS system, which is poor at the touchdown, and you have our bend stiffening device in the PSS. So the PSS has its own bend stiffener. So the bend stiffening device that we have here, one bend stiffener, but the CPS system typically also have a bend stiffening device also, but that is typically very poor here, whereas in the aperture part of the CPS is typically a very good bend stiffener, but it's typically a very poor bend stiffener when you come along the touchdown point.
Thank you. So you're already stiffening the area at the touchdown where you've got a lot of sediments.
As you see here,
Yeah.
yes, we have, yes.
Sorry, I just got a quick follow-up to that. In terms of your device, you're protecting the cable in terms of if we have a CPS failure in 30 years, but the cable survives, then we don't care about that. Or is the stiffener are you providing the stiffener to protect the cable, or are you providing the stiffener to restrain the CPS and therefore protect the cable, if that makes sense?
Yes, we both have, the PSS is two things. It's a bend stiffener for the cable, but it's also stabilization into the seabed. So it's two things. It's a stabilization into the seabed. So you have a stiff end of it. So it's a bend stiffener in a conventional way, where you have a stiff end away from the foundation, and also where we have the stabilization into the seabed with the screw piles. And you have a tip that's pointing towards the foundation with a flexible tip and a stiff end.
Okay, apologies, I should have introduced. I'm James Tate from TADEC. But my actual question before you started me having a whole conversation was, as someone's done a lot of analysis on CPS, I sort of feel that my opinion was that this is a combination of factors in terms of where people want to put wind farms, cable design, CPS design. Do you think that actually this is still a solution to a band-aid problem, and actually fundamentally from an investment point of view, people see pretty pictures of turbines above the sea, and the whole cable element is not thought of early enough? And could we go back somewhere else and start again from a CPS point of view? If you started again today, would a CPS look like an aperture coming out of a monopile 10 meters above the seabed, be buried 30 meters away?
No, I'm not sure if that's I'm not really sure if we could do the, if we could bury that. I think principally, I think the issue is today we tried to put the cable down at the seabed, and I think originally when the Danes did this, I'm Dane myself, so I can say this about the Danes. I think we put the cables down at the bottom because we thought when we did this to start off with that there would be no water particle currents down at the seabed. And therefore, I think when they start doing this, Henrik Stiedale and the rest, if you really interviewed them today, I think they wouldn't believe there would be any movement down at the seabed. And this is the reason we have the problem with the scouring, of course. And I think they were stupid enough. I think I can say this, or let's not say they were stupid enough. I think let's say they didn't expect, even when they had the problem with the scouring holes, they were actually that blindfolded that they think they were having scour holes, and they still didn't believe that they could have scour holes that were 13-meter deep in the UK sector, and that wouldn't impact the cables in the same place. So they were spending a lot of time and money on the scour holes that were 13-meter deep. They were having cables in at the very same place, and didn't spend 1 minute thinking, hey, we have cables in the same area, maybe we should start thinking about that as well. They didn't. So I don't think, but therefore your question is very valid. Yes, possibly one would have rethought this, but now, unfortunately, we have hang-offs of the cable and we have aperture holes in the monopile where they are. I think you have to think, we've been trying to remove various things in the hang-off of the monopiles. You can just forget changing that. So I think it's a good question. I think 10 years from now, nothing will be changed.
You're right in terms of the surprise. I've had clients when they see video or Flex models of things moving and they say they didn't expect that. And it's a standard.
What you can see here, what should change is at least lessons we learned in the industry. This best practice is made with input from Ørsted. Who built Hornsea 1? Who learned that the CPSs was filled with sediment? Who was building Hornsea 1? That was Ørsted. Why didn't Ørsted themselves tell the people that instructed Carbon Trust? It's actually Ørsted employees who are pulling this. Why are they not themselves ringing the bell?
Okay. Do we have any other questions? Yes, we have one here.
That's going to be difficult. I'm not sure I can answer that.
Actually, I wanted to actually publicly apologize to Henrik. At our last gathering in Copenhagen, perhaps 6 weeks ago, you asked me a question, and I'm very pleased to say, with my apologies, here is the answer.
No, is that the question?
Okay, I see some scribbles on a piece of paper. Yeah.
Thank you very much.
We have a question in the back.
Yes, hello. Yeah, very interesting product. I'm actually quite interested in the behavior of the screw piles,
Yes.
because of course that is subject to the same sediment changes
Yes.
of the.
Yeah. We started off with the screw piles, and with good help from some Danish professors, I went up to our Norwegian quarries. I was told that this worked fine in bedrocks, and therefore it would work fine in Norwegian granite. It took about 1.5 minutes to make a major flaw. Everything was a disaster. So I spoke to the Norwegian mining engineers, and they said, this steel you can use for building cars and building industry building and something, but never use it in a mine. So we had to rethink, and we then made a new patent pending. The reason why, if you go to our website, we cannot yet show you because it's patent pending, our bespoke screw pile. Our screw pile, we have demonstrated. You can also see a video on LinkedIn and so, where we drill this through 2 meters of the highest grading of scar protection, which is the grading is 60 to 300 kilo rock, which is the armor grading that's used on some of the wind parks. So we spent 90 seconds in getting to 2 meters of the scar protection. Then after we have drilled through the scar protection, we then start screwing into the seabed. Then we use data. We are then coupled to a cloud service where we measure then the torque and how we get down into the seabed. When we screw into the seabed in the North Sea, the typical screw pile is 3.6 meter long. So we then screw approximately 2.5 meters into the seabed below the scar protection. And we, after about 1.2 meter, we reach an anchoring strength of approximately 32 tons per screw pile. We continue down in the seabed to the full length of the screw pile depth. So each screw pile will have a minimum anchoring strength of 32 tons into the seabed. When we are into looser seabed, when we have mud, and so we have extension rods. So for example, in the Taiwan Strait and something where we may have scarring depth of 8 meters or something, we'll obviously have to use longer screw piles to get, but we can use this in all types of loose seabed or chalk. And so, whereas if we have real rock, we'll have to use rock anchors, and then we don't need to use so long screw pile. But we get always, when we drill into the loose seabeds, we have cloud service. So we actually provide you while we actually screw down the anchors, we get online anchoring strength when we get the screw piles into the seabed.
Okay, thank you. Do you need to equip your ROV with an extension or with a drill? How is it? I noted in your presentation that it is installed by way of an ROV.
Yeah, it's a special ROV. You see, it's a tracked ROV because there's a lot of torque in it, so we can't have a free flying. So obviously, this is a service we'll provide. So you will need to have a subcontractor that actually come with the ROV and the crew. So that will come on the back deck of a contractor.
Yeah.
Whether it's Jan de Nol that's in the room or whoever is Deep Ocean or whoever, is going to provide the
Okay, thank you.
installation. Yeah.
Good. But then, Henrik, thank you very much. We'll move on to our next presenter. We have some more questions, I think, but we'll take them during coffee. Perfect. So our next presenter is Matthew Lang from Global Maritime. Matthew.
Good morning, everybody. It's lovely to be here. I'm going to talk to you a little bit today about protection and primarily looking at the cable barrier risk assessment and talk a little bit about potential sabotage as well. So I'm a geotechnical engineer, so coming at this from maybe some slightly different angle than a few of the talks yesterday, looking at insurance, MWS, and some very interesting topics. So looking really at how we can use our information around soil models and soil information to get a good handle on how we bury and protect the cables. I'm from Global Maritime. A lot of you may know us, but for those who don't, we are a engineering consultancy which covers a wide range of different aspects, including marine warranty, which is where you may know us from, marine operations, marine services, and then my areas around the engineering, so engineering software, and my department, which is geoscience, that I'm going to primarily talk to you about today. So this infographic gives a bit of an information about what we do holistically, and I'm going to really focus on this bit in the yellow box down there with my role within the geosciences team as the subsea cables lead. So what we're going to talk about is the external threat to cables, how we assess the likelihood of occurring, primarily looking at potential for emergency anchoring and a statistical assessment using the CBRA to look at those, and then have a little bit of look at sabotage and the kind of the current press information that's coming out about how we protect cables, as we've had some kind of recent experience in doing a bit more of a deep dive into that topic from a cable protection point of view. Now, I probably don't have to tell the people in this room about the importance of subsea cables. I think we've heard about it quite a lot over the last couple of days, and probably most people spend most of their time, day jobs, talking about it. But as we also hear yesterday, cable damage is a huge part of what we are trying to prevent. Now, I look at it very much from a design point of view, typically. So in my head, prevention is better than cure. I know we've heard a lot from NKT and Jakob and other things yesterday about getting out and repair quickly. Ideally, we try and make it so you never have to do that, but sometimes it happens. So we've got to be prepared. But ideally, we'll look at it from this point of view. And we can see there that human activity aspects, which I think some of these things were touched on yesterday, and the sort of cost implications as well, of how important it is to understand what those threats to the cables are, and therefore how we can protect them, and what is an acceptable balance of protection against the risk level that we are dealing with from an insurance point of view and a warranty point of view. So typically the best way to prevent anything risk from happening is purely just avoid them. We talked about this with the UXO yesterday in terms of routing and how we can avoid much of these risks as much as we can. UXO being a prime one, which we showed yesterday. Boulders, I think there was a little talk about boulders yesterday as well. If we know where they are, we can route around them as our mapping constraints. Sadly, a lot of these threats that we have in terms of certainly external threats from human activity of anchoring and fishing are pretty prevalent across the entirety of the seabed, and therefore the best way to protect against them typically is burial, and then where we can't bury, if there's certain conditions, we'll look to do some form of external protection or other areas. So I think we talked about that with the inter-arrays yesterday as well. So not to teach you all to suck eggs, but for what the CBRA is, and again, we've just talked about the CPS guidance from the Carbon Trust. The Carbon Trust in 2015 released their guidelines along what the CBRA methodology should be and how we should use this sort of statistical assessment to establish a depth of lowering to adequately protect the cables. And really, we want to provide a framework and a guideline for how to understand that risk. And that's exactly what this document is. It's a guideline, it's a framework, it is not a standard which says you must do X, Y, Z. The actual methodology is relatively open as long as those risks are adequately assessed. And that's the way that we've approached our assessment of doing these things in terms of further detail within the aspects of how it's applied. So the standard CBRA approach, as I say, of what was that kind of done initially when computing power wasn't as good and we were looking for simplifications and maybe information and data wasn't as good going back into 2015 and beyond, was really quite a simplistic approach where we would try and group as much as we can, try and simplify the problem as much as we can along these long export routes, group them into areas of kind of similarity, and similarly with the IS data and the information we have about vessels, is bin the vessels into pots of similar sizes and really add in that conservatism through that method. So we've got a lot of large conservatisms where we've got some big areas where we'll just assume everything's quite similar, and the same with those binning of vessels. And we'll take that into the calculation in the top right, which is directly the statistical assessment we must perform from the Carbon Trust. But luckily, as we move on and technology advances, and I think all of us are using better technology in our day-to-day lives, we can really start to look at this from, well, what we've tried to do is look at this from a more geospatial approach, and a ground modeling approach and understanding the data first, rather than this grouping, and looking at it on more of a detailed level. So we can use quite a data-driven approach to create that ground model in 3 dimensions for the entire export cable route, interconnector cable route, or full lease area when we're looking at inter-array cables, and look at everything on a really discrete, detailed, granular basis. That gives us much more flexibility and much more options to look at things on a case-by-case basis and drill down into the data and the reasoning a lot more, removing a lot of these conservatisms. So that starts with a cable ground model. These are the sorts of things that I'm looking at all the time. I'm sure lots of you have come across them in many different ways. All the different data sets. We've got geotech, CPT stuff. We've got our sub-bottom traces, our bathymetry. And what we try to do is create an overall ground model from that for the full route, full area where survey is being carried out. So we'll be looking at the geotech traces, and we'll be trying to ground truth those against geotech. This is what's been done for many years in terms of foundation design and lease area design on a much deeper basis. But here we're looking at it from a relatively shallow top 6 meters, let's say, or slightly more in some cases with some sites. And we'll try and create a full 3D scope ground model, and we'll do that within a voxel volumetric cell model, where each cell within the ground model essentially contains the characteristics of the site from our integration of those data sets. So in the terms of the CBRA, we'll be looking at from each of those cells, we'll understand what soil type we've got, what strength that soil is. So we may have a clay of a clay shear strength of up to maybe 70 kPa. We may have a very soft clay down to 10 kPa. We may have a granular material with a relative density. And within each of those cells, that data is held and understood. And that all comes in, and we can see a sort of a zoom in of the zebra voxel cell approach there, where we've got all of that kind of geology information and bathymetry information in all of those cells, and the AIS data of what's crossing and what we're expecting historically from multiple years of AIS data input into the model. Now, each of those voxel cells, typically we work on a 50 by 50 meter XY grid cell basis, and we work on a 0.1 meter Z depth. And we'll compute that over the full size, so we can understand the full aspects of the site conditions. And then within each of those cells, we can run a similar calculation. So before, when we were looking at the old approach and we had those big areas and quite simplified approaches, we are calculating this P strike, and I won't go into all the details of it in a talk today, but it's all available within the Carbon Trust guidelines, and we can talk about it another time if needs be. But we can compute that risk in each of those individual 50 meter by 50 meter by 0.1 meter grid cells, or we can change the size of those, and we're very flexible in the way we can do that, but that's a sort of good size that we found gives us the benefits of what we're trying to do without overcomplicating the problem. And we can compute that within each grid cell at each time before we ever get a cable route. So we've got the full survey area, and therefore this can be used as a point of routing or just understanding your risk profile across the site. So here's an example. This is a fake wind farm we have created just to kind of depict these things, and we have this portal available for people to log in. So if anyone is interested in the CBRA and the way we're approaching it, please let me know, and we can eventually give you some an input into our WebGIS platform where you can actually look at our example wind farm, all open source data and a fake wind farm. Miri Domahanda actually is global maritime in Irish Gaelic because we built it on the side of the Irish coastline there. And really what we're getting out of it is a really detailed look at what the risk is. So we've actually extracted it along a cable route, but as I say, the full section of the site is actually being computed. So when we're pulling it out of that cable route, we can run multiple cases and run it all the time, but looking at it in section view is quite useful. And what we have here on the bottom is the grant model that you can see in the sort of light colors behind on the bottom panel. We've got a sort of very faint pinkish line, which is the computation of the recommended depth of lowering to get an inputted appropriate risk level along the length, which is an automated computation out of the model at a 50 meter by 50 meter square. Now, for any of the cable installation contractors or people involved in cable installation, I doubt you want to see a different DOL every 50 meters, so we try not to give you that. So we average that over a 500 meter length, which is that slightly darker, more bold and red color. So that gives an output, and in this instance, I think we're looking at a 10,000 year return period for the amount of risk over the entire cable length, and that is open to debate and interpretation, but it's sort of a rule of thumb historically of the industry, which we'll talk about a little bit. And then the green line is actually our manual input, which we're using this model to, and we can change that. And with the sensitivity of the model and the granular look that we're doing, we can actually, on that top right panel there, we've got the actually manual interface where we can define the zones after. I know we talked about removing zones earlier. They were simplification zones. These zones are a similar thought, but after the event of what we actually want to put in as a required depth of lowering to the installation contractor. So as you can see there's some action points, and you can add and remove zones, and you can change the burial depth. And actually, we'll look at an example in a moment where you can look at the P-strike profile in each of those zones for how it varies with depth to get a good idea of the sensitivity of it and understand actually what additional depth may require. There it is there. So we can look at one of the zones, and that's the zone on the very far right-hand side from KP, I think 20 plus. In this example where we can see how the actual risk develops within that zone over depth, and we can make a judgment call on that sort of cost benefit and use this in some good examples. So in this example, to get an actual real reduction in risk, we need to get down to that sort of 6 meter level. But when we're at 4 meters, if we are happy with that risk level and that interaction with the installation contractor and the developer, insurers, all of those areas, we can actually see that burying it at 2 meters gives basically the same amount of risk in terms of the full calculation of probabilistic assessment. So that cost benefit can be looked at in that way and really show that there is no real benefit of going down to 4 meters when we can just do 2. And that's been a huge saving across a few projects. This project I've tried to keep a bit anonymous, but you can see the sort of aspects on the left here where it's a much longer cable route, and therefore that cumulative risk along the full length of 10,000 years starts to become a bit more challenging just with the length of the cable. So we really need to understand that. And in this example that I'm actually showing, which is a real project example, not a fake one we made, the requirements locally from almost government were to go down to a certain depth up to 5-6 meters in this nearshore area. And we were able to use this, and with the detail and being able to show it and depict it very clearly, we actually managed to make the governmental bodies and consenting bodies reduce what they require, purely because they could see very plainly how that has impact on the actual risk and what the benefits of doing that are. So which was a real success, and really one of the reasons we developed the WebGIS was through that project and how that works. And then similarly, because we have this ground model with all this information in, we can use that for other things. So here we're looking at, and this is a very early feasibility look, we've got where we're looking at the panel here is looking at an inter-array cable and what tools we might use in a sort of traffic light assessment in different soil types. So we can put all of the information about soil types in, where boulder fields are, where we're seeing gravel, where our geotech samples are, and start to have almost like a live burial assessment, which we can update and adapt as we move through. We can also build in the stable seabed level and the sediment mobility across the top. So we can see here that our 0 line is at our reference or lower seabed level that we're expecting, and our seabed has been calculated below down to 1 meter, and we've got sort of sizes for cables, and then we've got a stable level above, and within our burial assessment we can build in all of that. So we can build in a lot of information very quickly and really analyze it in one way. Another way we can do this, which I think I spoke about last year, was putting in actually the thermal characteristics of the soil into this model as well. So once you've created that ground model and you've got that parameters in there, we can do a lot with it. So that's just some of the benefits of really doing it in this way and looking in this way, and the amount of conservatism we can really remove. The other thing about it is as well, once you've built that ground model, because it's independent of cable routes at that stage, it can be used through the full design, the installation process. So we can use it right off the get-go to input the as built or as installed live, and we can compute that risk straight away and use that to define areas of where we haven't achieved burial or target burial in the design phase. We can use it to look at whether we need to try another pass, whether we might have to do some external protection, or whether we won't have to look at that. And an example where we've actually used this on a project where that was the case, and we were feeding in the as-built data very quickly. If we went for the old approach, which is what the client was originally starting to do, of we didn't reach target burial, put rock there, and then we looked at it in this way and looked actually strategically where the risk is affected by those changes in burial, where we don't achieve, how does it actually impact the risk, and compute it along the route. We ended up with only a third of the amount of rock that the client was predicting from their own models. So we reduced the amount of rock by 2/3, which in that case actually prevented going over the consented rock allowance. So it was quite a huge impact that it could have on that project by looking at that in a lot of detail and removing all of that conservatism. Now, in my last sort of 2 or 3 minutes, I just want to touch on what the seabed doesn't really cover, and that is sabotage. We're seeing all of these sort of examples of recent things. We talked a little bit about this yesterday as well, of all these different areas, and really we're looking at emergency anchoring and fishing and all that sort of stuff in the seabed. And the sort of question is, how do you protect against sabotage in it? statistical way. I'm an engineer. This is what we look at. How do you predict it? Well, it's quite hard to predict. When is someone going to come along and drag something over your asset? And we've seen these examples of potential sabotage. There's a lot in the media about it, and there's a lot of information which is causing concern, certainly within the public and governments. And we know a little bit about the changes in the industry in terms of vessels that aren't very maintained. And there's an example which we can look at in a second of how that sort of looks at it. So here's a model, and I've definitely had, this is a live case of one of the sabotage. I'm sure you'll all know this case. I think it's even been mentioned. So I don't want to go into, so I've tried to crop out a lot of the information that I can't show, but I think hopefully there's enough in there to show it. And what has happened in the international water section, where a vessel, believed to be a Russian Shadow Fleet vessel, has damaged a cable, and the client has come to us and said, we never want this to happen again. Bury it deep enough so no one can damage our cable. You can understand what reaction that got, but we were polite. So we started looking at what actually the risk looks like. And actually, in the area where the damage occurred, they only cared about the international water section where cable vessels were particularly transiting. So in this 20-kilometer section in the middle from 60 to 80, we looked at all the geotech information, and as you can see, but hopefully see a little bit, the colors might be difficult to make out on the screen there, that it's very soft, or C1A, C1B, C1C, which is our very low strength clays, as ours. So you're talking 0 to sort of 15 kPa clays, very, very soft material, almost like a silty, muddy sludge type material. And as you can imagine, if you drop an anchor in there, it's going quite deep. It's very soft. It just allows it to pull through. And when we look at it from our risk point of view, so if we were looking at this in a design case, just for that middle section, and we buried the cable to 5 meters, we've got our green line there, which we've manually inputted, we can actually see that in that section in the middle, it's only a 1 in 1,000 year period at 5 meters burial depth that this cable will be struck by an anchor. Now, you insurers and people of that ilk in the room, are you comfortable with that risk profile over only a 20-kilometer section? I tell you that's about 10% of this cable route, so there will be risks across the rest of it. How would you feel about that risk profile? And then if I also told you that the cable was actually only buried to 1 meter initially when it was damaged, where would you feel worse about this risk profile now? And would you have accepted that? Now, we can see again that risk profile. If we look up at 1 meter, we've got even more risk. And you've got to get down to 5 meters just to even start to see a slight lowering. And even then, we still have a hell of a lot of risk. We've got a lot of huge cargo tanker vessels going over this and some very soft things, and it's happening regularly. So there's a big debate there of, was this cable sabotaged or was it just not adequately protected? And that's not for me to decide. I'm no expert on geopolitical incidents, but there is there's certainly looking at this. If I was asked from a design case at the very start to design this cable, I wouldn't have suggested 1 meter, and I don't think many insurance companies would have accepted the 1 meter, looking at the risk profile that they were having to stomach. And I know there's a few people from the ESCA place. I actually stole this from Peter Jameson at the last ESCA event up in Edinburgh, where he did quite a long talk on whether we think sabotage is a real threat and how we should deal with it. And I thought this was quite a funny quote in the way of looking at it, especially off the back of the sort of investigations we've done. And I think we've talked a lot about what can be done to protect it, even if we can't necessarily bury it hundreds of meters deep to make this never happen again, as we were requested, which I don't think is going to be the outcome of the repair on that one anyway. So I think that was pretty much everything from me. Just to highlight the sort of aspects we can have in the Zebra and the work that we're doing. And yeah, thank you very much for listening.
Thank you. So do we have questions from the audience? I'll ask some of my own, and you can give him the microphone. But doing this Zebra assessment, you also look at the economics of it, and you mentioned reducing the amount of rock placed or installed. when you look at the risk reduction, does it economically ever make sense to do remedial burial or additional protection? Or is the reduction in risk compared to the price tag of doing that insignificantly low?
It depends on where you are, and I think it can be a little bit of a case-by-case basis, which is why we look at it try to look at it in such detail so we can really understand it. We have a lot of cases where, yeah, we do try and look at that economics and certainly that cost benefit of, I can name an example recently where we've been in what is primarily a sandy site, but just below that sand layer is very, very hard till material, which is great to prevent anchors going into it, but terrible for if you want to install in it, especially if you've got a lot of sand and you need cutting tools and the sand gets in the cutter and it causes a bit of a risk. So there's other risks that have to be considered holistically in terms of actually the cable installation and what the benefits are. So what we can essentially do very quickly is look at, well, the benefit may be to just lie on top of that and just have that sand coverage. And yes, in some areas you may have a slight reduced burial, but what actually impact may that have? We've still got adequate protection from fishing and cover that we're not going to have stability issues or anything like that. And what therefore is our overall holistic risk, and look at it from that case of where the cost benefit is. And similarly, when we're looking at external protection, where those points are, which those pinch points of, yes, this is definitely an area where it's needed because this is an important critical risk area. And this is an area where maybe it's not as critical. And therefore you have 0.5 meters of cover here. We wanted 0.7. We don't think there's any need to do that and have a look at that as a big cumulative effect.
Okay. Henrik, you had a question?
Is it on? Yeah. For the burial risk, there was many years ago, there was a lot of discussion. I think I don't recall if it was Dodge or the Belgium developers that had this discussion whether to look at this anchoring damage and so. But of course, with mobile seabed and looking 25 years ahead, if you only have it buried 1 meter deep, you can take very little scouring or global scouring before you need a fishing vessel. And then if you have an anchoring where you have had a fishing vessel, so that's really, to use your own presentation, you need you are cutting it very thin then in that particular area.
Yeah, exactly. And really, when we're looking at the sea burial, we are looking at what depth we needed below that LSBL or non-mobile level. So ideally, that will be an input into the model as a whole. What we maybe conservatively do as a first pass is almost to strip off the mobile layer and say where we are burying it below that, knowing that therefore when we compute the risk, there is always going to be some amount of that additional soil above because it won't have been removed throughout. And I think we showed that within that BAS section where we've got that zero line as our start point of the zebra and we've got the mobile layer above. So yeah, so we've got to take into account because exactly that, what is the risk in year 1 when we have all that lovely sand above, and what is the risk in year 25? Maybe very different things. And again, you can almost compute that at any depth of burial survey throughout.
Also, as they say, there will be a big difference between the export cable and the inter-array cables because, I mean, for a fishing vessel, having an anchor that will actually stick more than 30 centimeter into the seabed is quite unlikely. And for a bigger vessel, I think the risk for an anchor may be the least of the worries inside the wind park.
Exactly.
If the vessel first comes into the wind park.
Yeah, and it's which vessels are going into the wind park and yet fishing. And we see this in different areas of the world as well. You're looking, I think in Denmark, you aren't allowed to go into a wind farm at all, fishing vessels, but we see it happen. So officially, if you just follow the guidance, let's not protect against those fishing vessels. But when you actually look at the data, you have to protect against those vessels and make sure it's down to a certain depth. So it's really just understanding that on a whole view.
Okay, but then, oh, sorry, we have
one more. Can I do one? Thanks, Matthew. Some of I like the line diagram looking at different tools for burial. And it goes back to some years ago when we had the BPI before the CBRA and the Barrel Protection Index and the way we were working. Some of the challenges you've got typically on longer systems is that mobilization. What is the right tool? Because you're only going to mobilize once.
Yeah.
Trenching, typically, you might go twice. You might put 2 ships out there if it's for the cost benefit, if it's there. But some of the best trenching systems I've seen have been 2 tools on one ship, and they switch them between them. So you're doing jetting or you're doing cutting back and forth, and it's all post-lay. And obviously, if you're doing a plow and then a post-lay jet burial for the bits, the skips and the bits you didn't quite get it down.
Yeah.
In an ideal world, you'd have like 3, 4 different tools, and you'd be able to get it. I think where I'm getting at is it's a lovely piece of analysis and a great theoretical tool, but when you get it to the cost of actually putting the cable in, installing it, what are you actually mobilizing? What kit are you going to use? What's going to be most beneficial to it? Where do you draw that average line? So how do you get from the perfect example in your model to what the real world are going to do? And this is where the CBRA came in with when Catapult, was it? Carbon Trust did that, which was all about bringing the cost down. You know, where do we find some sort of medium level that will be acceptable to industry?
Yeah.
But is it enough? And if we're looking at interconnectors, generally not. It might be all right for the wind industry, but it's probably not adequate. And we're seeing that in some of the examples you've put up. So how do you get from theory to what's really acceptable?
Yeah, I totally agree with you. And I think that example shown there was very early phase of a project for the developer. So before they're going out to tender to the cable installation contractors, and the plan is always that they come with their solutions of we think our tools will work and this is what we would be doing, and therefore they can go, well, they've said we're going to cut all of this and we don't think it's necessarily ready for cutting and that sort of thing. So yeah, I think you're totally right that there is a next step that takes that on into, and that's what we try and add the personal value to it. And luckily within Global Maritime, we've got master mariners and we've got cable operations people who've been out and done the installations and been parts of those companies, and we try and bring in that actual personal experience to it as well. So we've got the theoretical part, and we go, well, you're not going to have 4 tools and all in 3 ships running behind you. This is actually our plan of installation that we run through, and we'll look at that from where we are building that in. So yeah, I think you're totally right when we get to that point, especially if reviewing those bids that we look at, and we support on that sort of aspect quite a lot with our clients as sort of owner's engineer when we're supporting the cable installation contractors, saying, yeah, we'll install it with these tools, and we can take that away and look at it and can really start to find that whole model.
Thanks. It's the art of compromise.
Exactly.
Right. But then thank you very much.
Thank you.
And we'll move on to our next presenter, and that's going to be Chas Bradbury from Peritus International.
Brilliant. Thank you. Thank you for having me here. Now, although this is the purported agenda, really, what I need you to do is to cast your mind back in a kind of Twilight Zone-y kind of way, not too far, let's say maybe 30 minutes, when James asked this brilliant question, and he said, what happens if we actually stop and think, do we really need a CPS? What would it look like if we just went right back to the beginning? And this entire presentation basically is focused on you and answering that question. So thank you very much. Probably the best setup I have ever had at a conference anywhere. A little bit about Peritus, because I'm in charge of business development and I'm not very good at my job. So we are an engineering consultancy, subsea engineering, and we've worked with a number of the major players doing all sorts of wind farm odds and sods, but mainly with cables, a lot of cable crossing, cable stability, and very recently doing a lot of work on cable protection systems. So this is some of the things, and and again, Henrik's presentation was brilliant and really set the scene really well. So these are some Orcaflex modeling of unprotected cables, and you can see the cables moving, and we don't want the cables to do that. This is another animation, which it's just about playing, and you can see the cable moving, and this is partially protected cable. And what happens when you apply the wave and current to the cable? It moves, it causes fatigue in the cable. There is potential for direct wave action, and there's also potential for some VIV, although that is limited on the cable. But I'm not going to spend much time on this because I think we all know it, but basically the cable at that interface between the monopile or the jacket and the seabed has to be protected because we want to avoid that movement. We want to avoid the MBR exceedances, and we want to avoid any kind of fatigue issues. And then, so this is the question, why do they look like this? And this again, from the Carbon Trust document, which then we remodeled for some work. But there's a whole load of components in there, from the stiffener, the latch, bend restrictor. There's a load of stuff, and all of these bits and pieces obviously have to be added to the cable before it can be pulled in. So yeah, the absolute question that I'm trying to answer, and that we were asked to answer by a client, is why? What do we actually need? Is the question. Why are we going for this? Especially, for instance, if we are, if the decision at the end of the day is to rock dump everything, well, if we are going to rock dump it, do we actually need any of this before we put rock down? What purpose does it have if the cable is then shielded from all wave and current activation as life goes on? So could, for instance, could it look like this? Could we just dollop a great big grout bag under the cable? Would that give it sufficient holding capacity to stop it from moving around too much? Maybe. Could it look like this? Instead of a grout bag, very similarly, we could just have a solid support that we slip under, which is large enough to hold the cable still. It will break up any free spans, it will stop it from moving, it will stop your MBRs being exceeded potentially. Or how about a shroud of some description? What if we put the cable in a frame? Would that stop it from moving? Yes. Obviously, there's other issues with this kind of thing. It takes longer to fit. It has to be designed, all sorts of things. But actually, it is a perfectly acceptable potential option. The reason there's dimensions on these is because we looked at all of these for a project. So these were designs that we came up with to see what we could do instead of a traditional CPS. Another shroud, but this time a fully enclosed shroud. Again, been used in the past on oil and gas type projects. Would have the same benefits, would stop your cable having any hydrodynamic loads applied to it, would reduce the bending. A whole back clamp. Now, this is not dissimilar to Henrik's thing, but it is generally higher up the cable. So this would be maybe 2/3 of the way up the free span and holding the cable with a chain back to the monopile or back to the jacket. And it could just be one, it could be several of them. again, tried and trusted solutions that have been used in industry for a while. We could put weights on it. We could change the shape of the cable as they do with floating wind, with buoyant sections or heavier sections. So we could effectively engineer the most optimal shape of the cable that we might want, that we might like, in order to protect it for its life. And these, in terms of avoiding VIV, you put some strakes on it, and you see these. These are used in chimneys and lampposts and all sorts of things. It breaks up the fluid flow over the cable, stops there being any kind of vibration. So again, it eliminates part of the problem potentially using these instead of using a traditional CPS type system. And there's a lot of stuff written about it, and a lot of design codes, and they overlap, they contradict each other. And I will agree as well with Henrik about the Carbon Trust CPS design code. It provides a kind of good overview, but it doesn't delve into much detail. It doesn't give you, for instance, design limits, or what the limits on your bend restrictor should be, or what the friction coefficient between the seabed and the rock and the cable, the rock and the cable should be, or any of those kind of things. It is quite generic overview, and its initial starting point is we should have what you'd call a traditional CPS system. It doesn't take the step back and says, well, okay, what do we actually need? What is the problem we are trying to solve? And what tools have we got that might solve that problem? So there are some issues, and again, I don't want to do this to death, but there are issues with bend restrictors failing. There are issues with the MBRs being exceeded during the pull-in. As I've mentioned already, VIV and direct wave fatigue are issues. There's this kind of whipping, I'm almost breakdancing, there's this kind of whipping phenomena that occurs when you have these unsupported sections, and I think that was slightly unexpected by most people. But again, it's quite a well-established and well-known phenomenon now that happens. And there's abrasion as the CPS moves on that little animation I showed, which was a protected cable. You could still see it moving across the seabed, and there is abrasion that goes because it's very rough rock potentially that this cable system is moving on. And they are fragile. They will not withstand an anchor strike or a dropped object or fishing gear or anything else. They are fragile systems. And because they move sideways, as we've said, quite often there is rock or rock bags put on top of them to stop them from moving and to hold them steady. They are an additional tube which can give you thermal restraints, and as we've said, that they can fill with sediment as well, which also causes issues. And they do take their time. They cost money to buy, they take time to install, and they need to be maintained or even replaced, as we have heard. So that's when we were asked to look at the question, what do we actually need? Why are we doing this? And so we do obviously need some protection at their interface. There is an unsupported section between the seabed and the monopile and the jacket, which does need some protection. We need to ensure that the cable is not overbent as it is installed. We need to ensure that it doesn't suffer from VIV or from any fatigue issues. We need to ensure that it stays where we put it. We don't want it moving around with the wave and the current stuff. And as I've just run through, these are all the things that we need to consider. So when you're coming along to design a cable protection system, you need to consider all of these factors in the design of it. So this is a deliberately obscure picture at the bottom. We were tasked by a client to develop a design guideline for them. Now, this wasn't a design guideline to, the ultimate yield strength of the whatever has to be 80% of the stress, and it was none of that kind of stuff. This was a designed guideline, as in, well, okay, what do we need? What should we be putting down there? If we are going to put rock on it, do we need a bend restrictor? If we are going to do, I don't know, if depending on how you're going to pull it in, do you need a kind of latching mechanism? Do you need a centralizer? And so we went through this whole process with them and created this design guideline. And I asked them if I could share it with you, and they said no. So I've put a little picture on it because the solution is not being looked at as a whole. There is no kind of like optimum solution. It's always, well, okay, we need one of these cable protection systems, and then maybe we'll put some rock on it, or we'll do something else. No one says, well, okay, if we take these bits off because we're going to rock dump it, what else do we actually need? So we developed this guideline to kind of solve these problems, and I am hopeful that after a while, when they come to market with their because this is a live project at the moment, and they haven't gone out to the market for the cable protection systems yet. But when they do, that they will be more inclined to share this, because I think it will be useful. And one thing it does do, it splits cable protection systems into what we call the CPS, which are things that you attach to the cable. And we've termed this kind of slightly new term called the DPS, which is detached from the cable. So that would be things like rock dump or mattresses or rock bags. So you provide your protection from a DPS. We were going to call it EPS, external protection system, but it sounded a bit environmental. So we opted for the D, detached from the cable protection system. To have a look at. Oh yeah, now this is an air fryer, which sounds like a slight segue, but it really isn't. Back in the day, when I used to go home for my tea, my mum would be there, and she would have this great big boiling pan of fat on the stove. And into this boiling pan of fat, she would stick my sausage or my chips or whatever it was. And these things used to catch fire. And there used to be loads of adverts on TV about what to do if your chip pan catches fire, and everyone had the fire blankets, and you probably remember you have to wrap it around your hands and do this, and you shouldn't put water on it and everything else. But we don't have those anymore. We don't have those adverts anymore. We don't have those big pans of boiling fats in people's kitchen, because the air fryer came along and changed it. And this is what I am proposing. Now, this is a completely real image and not in any way generated by ChatGPT, of Jennifer Lopez on a wind farm holding a cable. And the reason for that is so you remember something called J-Lo. And this is J-Lo. We have figured that actually, if we lower the J-tube on a jacket, we no longer need a cable protection system. The J-tube can sit on the seabed floor, then actually we don't need any of this stuff. And we can just put some rock bags on top of it, or a mattress on top of it, or something else. And there is literally no need for a cable protection system. There is no fatigue. There's no abrasion if we drop something on top of it. It's quick, it's cheap. It may be slightly harder to design. So this is it. Really simple. Really simple. But the main reason I'm standing up here today is because we are trying to get some funding to develop this a bit further. And I've spoken to a couple of people about it, but I've got some meetings in a week or so with some actual funders. So I would like to get any kind of objections or things that might not work from you guys, so I can then formulate an answer or a response to them to take to the other people. So I'm basically crowdsourcing your immense knowledge. But so that is basically the end of my presentation. But if there's any feedback on why lowering the, not for monopiles, I don't think, because they still have the hole cut in the side, but any feedback on why that should not work, just lowering the J-tube for a jacket or a substation would be really appreciated. Thank you.
Thank you, Chaz. If you could put up the video maybe again, then we can
Yeah.
poke holes in it.
This one?
Henrik, yes, okay. Yeah, you're done. Forget it now.
Well, no, it's probably the most exciting video you've ever seen, that.
Well, it looks very much like a certain Danish company had a perfect idea about a couple of years ago with the swinging J-tubes. And this was at the time when British diving industry was seeing a perfect future. And it sparked a number of headlines in papers in UK, because then UK diving industry were going to need 1,000 new divers, because these swinging J-tubes, they needed diver support, because this worked fine in a garage, this patent. And you also may know that the first J-tubes that were designed in Denmark by Ramboll, they were telescopic J-tubes. And these telescopic J-tubes, they worked fine in the yard and in the testing centers. The thing about when you build offshore wind, the best place to build offshore wind is on land. And when you put them in a stupid environment, for example, offshore, things are a little bit more difficult. And this looks easy, what you're doing, so I can only say good luck. It's been tried and tested. Look at what Ramboll did and look at why it went sorely wrong.
Yeah, I mean, there are some differences here. I mean, we are planning to use a torque bucket with a rack and pinion, so there's no divers needed. It's just ROV.
I can tell you, Ramboll's thing was not intended to use divers. The divers were there to fit things that went sorely wrong.
Okay.
Do we have any more comments, questions? Then I'd have one, Chaz. I understand that this happens during installation before a cable is pulled in.
Yeah, immediately before cable's pulled in.
Yeah. Then 20 years later, what will happen with this? Will we expect this still to be on the bottom, or things to move and then cable getting exposed?
Well, if it's going down onto scour protection, then it shouldn't. The scour protection should remain in place. It should rest on top of it. You stick a couple of mattresses on your cable and hopefully it will stay in place. So as long as your scour protection is working, this should be fine.
Yep. Okay. Okay. One more?
Yeah, there must be some actual bigger objections to this.
Did you consider using an internal J-tube?
Using what, sorry?
A J-tube inside the monopile?
No, not for this, because I think monopiles will always, at the moment, I mean, they have a hole cut in the bottom of them. Yeah, which obviously there's a structural penalty on the steel there because you're cutting every chunk out of your monopile. So at the moment, and the wind farm we are kind of looking at this for is jackets based. So at the moment we're looking at jackets. There is no reason maybe why you couldn't have something that extended out of the monopile in a similar way to this. But I think also the way the monopiles are installed with the piling and the fatigue, actually, it's very difficult to have anything that attaches to the monopile pre-installation. So I think
But the same
more
concept. So you also use this telescopic thing and you install the J-tube, internal J-tube after the monopile is installed.
Yeah, you could do that. You could do that. But I think at the moment the focus would be on jackets. But yeah, absolutely. If you wanted an external J-tube on your monopile, you could do that.
We could have one more comment in the back and we take that during the break. Okay? Yeah.
Yeah, Andrew Hunt from Spiralis Energy. I thought I had problems trying to find a dynamic cable for a tidal environment. And I'm sort of, I don't know whether I'm encouraged by the number of problems I'm still hearing about in offshore wind. But just to get back to some of the comments from the presentation here, Henrik mentioned something about the J tubes or the CPS systems filling up with silt. Would that, to me, would be perhaps a problem for this solution as well? Or?
Yeah, I mean, potentially, but I think arguably if the J tube was 3-4 meters above the seabed before it was installed, lowered down immediately prior to installation, and then the cable was not sitting in a CPS, the cable would be sitting under a couple of concrete mattresses. So there's no abrasion going on, there's no movement going on. There's at no point is the cable really exposed to allow it to move. So yes, you may get some sediment in the end of the J tube as you pull the cable in, but I think long term that's not an issue because it's not abrading against that sediment. But worthy of consideration though.
Good, but then let's move to the next presentation and we'll poke some holes in during coffee. Yeah. Okay, but then the next presenter is Adam Caton from Turn Energy. Adam.
Good morning, everyone. Thanks very much for having me here. So my name is Adam Caton. I work for Turn Energy. So today I'd like to talk a little bit about a study we did supporting an offshore wind developer on sort of a live CBRA support during the trenching operations. I'd like to apologise a bit as well because I think there's going to be quite a bit of overlap with Matthew's presentation here. So I'll do my best not to just repeat everything he said. Where's the thing for? Yeah, apologies. So I'll begin with just a little bit on who Turn Energy are. So our experience. I'll then do a very quick study, view of the study we did. So just a quick overview. I'll then take a small step back and just talk about the CBRA, but I'll do that at a very high level because you've just heard about that about half an hour ago. I'll then talk a little bit about so what we're seeing more in tenders in terms of what we've been required, what's sort of requested to do by various clients, generally say the offshore wind developers. Sort of the approach and sort of some of the limitations we're finding, we're just sort of doing it this way. And then I'll sort of go a bit more into the live CBRA and the benefits we're finding. We found we're doing it, a lot of this stuff offshore. So Turn Energy, we are an independent and fully integrated marine geoscience consultancy. We consider the independence and the integration sort of key parts of our business, really. The independence means we're not really owned by anyone, so we can be fully independent with all our decisions and all our recommendations. And obviously integration means we pull together various geoscience, geotechnics, geophysics, GIS into every project, and CBRAs are a really good example of that because you need multiple disciplines to really understand the hazards you're facing. Our mission really is to understand and manage and mitigate the seabed risks for the projects. Ultimately, the purpose is to support the delivery of the energy transition. We don't shy away from oil and gas. We do a little bit of oil and gas still, but most of our work, I would say, is renewables these days. This is just a small selection of some of the clients we've worked for recently. This is just our cables. We do a lot of foundation design, spud analysis, things like that, but these are just some of the cables projects we've had. So recognise a few developers on there. So the EnBW, Scottish Power, Ocean Winds, RWE. Obviously, we've worked with Subsea 7 and Ithaca as well. These are sort of over the last sort of 12, 24 months, something like that. So in terms of cables experience, we do quite a lot of route engineering studies. So that's mainly sort of GIS driven, really, because that sort of is where you draw out the routes. We do our cable burial risk assessments, CBRAs. We then move on and do a lot of burial assessments. That sort of follows on from the CBRA. We do live or as-built CBRA support. And we also, because of our independence, we finally get a lot of expert witness work as well. And I don't have to tell you guys this, but 90% of it is cables related. As we said, has been shown over the last few days. I don't think I can think of a single expert witness project not being cables related in the last 12 months. So the case study summary, the project began with us doing some CBRAs for a client. I can't really say the name of it, unfortunately. So this was for export cable, an interconnector, and the inter-array cables. Following delivery of those components, we were asked to provide as-built CBRA following the trenching operations. But when we sat down and sort of discussed with them what they actually wanted, it became very clear what they wanted was more live support. Like while the trenching vessel was on site, they wanted us to sort of live assess the risk to the cable based on the depth of lowering they achieved. So the ultimate goals really were to try and minimize multiple passes, try and assist with minimizing any rock dump they needed to do. But the critical thing was there should be no increased risk to the cable based on any decisions or any advice we gave. So this is all based on sort of the results of the CBRA, as you'll see in a minute. Okay, so I'm going to go through this very, very quickly. So what is a CBRA? It's an assessment to help define appropriate depth of lowering for a cable based on the risks. These are normally divided into two sections, anthropogenic or natural. Anthropogenic being your fishing, your shipping. The natural hazards typically being mobile sediments, but you can have other hazards. Sort of if you get really unlucky, you can have creep features, things like that. The key component is the probabilistic assessment, as Matthew went through in a lot of detail. We again follow the carbon trust one. So other hazards as well are normally used, so they need to be identified accordingly. So things like your fishing risks, they don't really come into your probabilistic assessment because it's a different type of hazard. But we would normally use that to specify what's called your minimum depth of lowering. So you should never leave a cable on the seabed because that's how you get most of your problems. So you should always have a minimum, and that we normally use the fishing risk to set that. But again, creep, things like that can also affect that quite a lot. When we're doing our assessment, we'd like to present the results as per these graphs you can see here. So the advantage of presenting it this way is the client can actively see how their risk level will change depending on the depth of lowering. So they don't have to redo the whole assessment if they say to begin with, or we want to target X depth or X return period. And then as they speak to their own sort of legal team, they realize, no, that's not going to be enough. We need lower risk than that. They can see themselves very quickly what depths they have to really achieve to reduce that risk. So just to quickly talk through to the graphs, the top one, that's a sand profile, I believe. So what that really shows to the client is if they want to make any more meaningful impact to the risk level to their cable by burial, they're looking at burying to at least sort of the 1.8 sort of meters. We normally present all our data in return period, which is, I believe Matthew I think he used frequency for his presentation. They're essentially the same thing. This is just number of years statistically to get a strike, really. So he presents the same data is presented slightly differently. One thing to note as well is I appreciate the legal people in the room might hate this, but it's not always possible to bury that cable to completely remove your risk. Is it worth it from a statistical point of view? Is it worth it from the problems you're going to have on site trying to do it? So as you can see for the top graph, if you want to bury to completely remove that risk, you're looking at 2.5 meters burial, which you could argue is achievable. But what problems are you going to encounter trying to do that? Depends on the ground conditions, things like that. And obviously, the more passes you try and do, the more you're handling the cable, the more risk you're going to have. So the bottom graph is it's sand over soft clay or very low strength clay. The advantage of, well, unfortunately, on this particular example, they didn't quite get this lucky, but especially in near shore section, we got high numbers of very small vessels. You can potentially remove a lot of your risk by if you've got a sand over a low strength clay profile, you might be able to remove a lot of your risk just by getting below that sand because the sand will be sufficiently thick to stop a lot of those anchors. Unfortunately, in this case, it wasn't because you can see a few anchors that got stopped statistically by the sand, but then it just ran away. And just, as the anchors started to penetrate into that lower strength material, the depths became so unreasonable that there was no way you're going to realistically protect by burial. So the current approach, it's what we're normally being asked for these days is sort of as-built trenching support. This appears in all the tenders. It really takes the achieved depth of lowering. It highlights high-risk zones, proposes remedial work to reduce the risk. It can also be used to predict future risks. So if you've got a monitoring program going, you can see how your mobile sands, things like that, mobile sediments might be affected. These studies are very useful. We're not saying they're not. They've been a very important part of any sort of protection of any cable. But we feel there's a few limitations with doing things once you've finished on site. There's a few things you can address when you're there with the trenching equipment. The image there is just an extract from, I think, a Kathy's paper where they talked about this. This is just showing how mobile sediment can change and how that deburial almost can affect your cable. So it is very important to monitor these things. So the limitations really of doing things, well, trying to do everything once you've left site. It's too late once the vessel's really left to start thinking about increasing your depth of lowering. You know, once you've gone, it's going to be very expensive to go if you have to go back and remobilize any trenching equipment because you realize you've not achieved what you need to. So the ultimate question is, can any parts of this as-built CBRA be done whilst you're there? Can you actively live assess the risk to your cable? And can you actively try and reduce as well your second pass trenching? And we think there's a lot of value in doing it this way. So as I said, this is a study which you do when you're actually on site. The ultimate aim is to reduce, improve efficiency on site, really, but also reduce the risk of any remobilization. If you want to do this assessment, it's fairly straightforward. All you need to do really is we need the as trench data from the vessel. We need the defined target depth of lowering. That's normally divided from the CBRA or provided by the client. Typically, they will tell you what they're trying to target. You need to establish what your minimum is. What's the absolute minimum you're prepared to accept? We would normally define it by fishing because of the high risk that presents. But so there's other ways you can do it. You need the CBRA results. So a fully zoned route with risk profiles as per those previous graphs. That's why it's so important you present it that way, because you need to be able to track that risk with depth. And also, ideally, you need the specification of the trench equipment, because the last thing we want to do is start suggesting you do a second pass when you're in high strength clay with a jet trench or something, because you're going to struggle really to achieve much more depth really at times there. So this is just an example of an output from the vessel that you can get. This is how we would, this is the initial stage for us where we would start breaking down and seeing what we've actually got in terms of sort of trenching depths. I wonder if I can use this. So the black line is the key one. So that's your achieved depth of lowering. The other key things we've marked on here are, so your bottom dotted line here, that's your minimum. That's the absolute bare minimum the client's prepared to accept. So obviously if you're not below that, then serious issues, you're going to have to think about either definitely doing another pass or additional protection. If you're above the target, again, don't have to do anything. You've achieved what you needed to, but it's this kind of grey, this area in between. What do you do here? Do you go back into the past? Do you immediately look at rock dump, or is it? Are you able to accept the risk at this level? So the process we kind of follow when we're looking at, when we get the data in, is we'll look to, obviously first we'll check, have you achieved the target depth of lowering? If it's yes, everything's fine, move on to the next section. If you haven't achieved the target, have you at least achieved the minimum? If it's a no, you're going to have to start immediately looking at, can the trench go deeper? Is it possible, even possible to do another pass? If it's a yes, then you probably want to look at another pass. If it's not, then you're going to have to look straight away at remedial work, because there's no value really in trying to go back with a trencher and keep repeating in ground that it's not going to be suitable for it. If you have achieved the minimum depth of lowering, this is where you need to start thinking and discussing with the client, what is your residual risk now? Is the residual risk, have you now increased the risk to the cable by not achieving that target burial depth? Is the client now comfortable with that risk level? If the client's comfortable and you think you can't really achieve anything more with burial, then yes, move on to the next section. If it's a no, again, you're going back into that loop of, right, can we go deeper? Is remedial work now required, or can we go back and perform an additional pass? I sort of did a worked example almost here. This is kind of a bit of a made up scenario, but hopefully it will demonstrate what I mean. So the client wanted to target a meter. We decided the minimum was 0.6, just to account for the fishing risk. We achieved 0.7, which is just over the minimum, but again, a bit away from what they actually wanted to target. But if you look at the, actual depth profile, there's no difference in risk between a meter and 0.7 here in terms of the statistical risk to the cable. So you have to ask the question of what is the benefit in going back and trying to handle the cable again, try and go back into it, try and do an extra pass to get extra lowering. If the client's still not comfortable with the risk, then you're not realistically going to lower it any further with trenching anyway. You're going to have to immediately start looking at additional protection, because in order to make any meaningful impact to that risk level, you're going to have to go to your 1.8, which is almost double what your target is. So in this situation, our advice to the client will be, if you're comfortable with the risk level, move on. If not, you need to start immediately thinking about remedial protection. So in terms of what outputs you would get from us doing this study, we'd normally get results back within 24 hours. We try and get it back even quicker because we were looking at getting client reps on board, sort of working on this. So potentially you can have recommendations within hours, pretty much, of the pass being complete. You'll get a summary table detailing the residual risk to the cable based on the depth of blowing you've actually achieved. We find this is quite a nice output because we appreciate a lot of the time, lots of developers don't actually own the cables. They obviously install them, then they hand them on to other people. And if you can demonstrate what your risk to the cable is, you've done everything you can to protect it. That's quite a nice document just to present that. You'll have your targeted rock dump recommendations. So that would just be detailing where we think you need to keep going back and do or remedial work, I guess, not just rock dump. Where we really need to go back and think about additional protection areas where you think, based on the risk level, you can probably avoid it or not have to do it. Obviously, get a summary technical note detailing what process we followed, the recommendations. But the ultimate output really is you're potentially going to save a lot of time on site by removing, just going over the same areas over and over again to try and get a marginal or negligible decrease in risk. And you'll also significant reduction having to go back and potentially remobilize a trencher again once if you realize during the following the site work that your risk level is still too high. So this is just sort of again an example. You can see, let's see if I can get the thing to work. So the way this sort of is set out is you've got your target depth of lowering, that's your anchoring risk. We determined the anchoring risk, that's what it was defined by in this. You've got your fishing risk, which is defined as the minimum. So these columns here sort of present what your risk level is at that they've achieved and the risk level based on the CBRA at a meter. So I guess a really good example, this is a 3E one here, where we didn't really achieve the target depth of lowering at all. We completely failed to do that, but we actually hit the minimum, so that was fine. When we actually checked that against what the residual risk was, there was no change. So our advice to the client was, if you're comfortable with this risk level, move on. So potentially save them a needless additional pass, really. So just one last little bit on, I guess, the cost benefit. Some costs there in the bottom corner. They're a little bit out of date. I think these are sort of from the 23, 24 sort of time, but don't tell you they're quite high. You know, when you're on site, time is ultimately money. You know, less time you can spend there, the better. Especially doing trenching ops, because it's not just about number of days. Uncertainties with weather. A week campaign can quickly turn into a month if you're really unlucky. You've got the saving on the vessel remobs if you have to go back. You know, £500,000, you know, $500,000, very quickly can spiral out of control. You can very much reduce your rock dump campaign. If you know what your risk is, you can very quickly start to reduce that and start doing more targeted rock dump. So potentially huge savings there, because again, it's not just the rock you're paying for, it's also the transit between the quarry, it's the weather downtime, all of that plays a huge impact on it. You've got potentially a small environmental benefit if you there's less time on site, lower carbon footprint. We've got potentially assistance with decommissioning as well. If you reduce that rock dump, you're potentially not going to have to do as much decommissioning if you have to remove any of your like concrete pads and things like that you place down. On this project, it was very difficult to really assess how much we really saved the client by helping them, because we don't really know what they would have done without our input. But looking at that table, it doesn't take much before the savings were potentially in the millions, you know. So I think that's it. And I don't know if that's going to work, but it's a QR code to our website. It worked when I tried it.
So, do we have questions from the audience? Al.
Thank you very much. That was an extremely thought-provoking presentation. Congratulations, you have succeeded in convincing me that cable trenching and burial is fraught with hazards of not quite getting it deep enough and spending lots and lots of money. So I want to say thank you. And at risk of joining Chaz in the naughty corner for presenting crazy ideas, I am wondering, why bother? Why bother burying the cables? And so I want to say thank you also to Lars Andre for his presentation yesterday, where he talked to us about the Saint-Nazaire project, where they didn't bury a single kilometre of that cable. It's left exposed on the seabed forever. It's encased in cast iron shells. And the lay rates they got, they were way up there, competitive with all the other cases he put up there. So why bother burying cables? Have we missed a trick here? Can we just, like also acknowledging Matthew's talk just before, through the Baltic where you've got meters and meters and meters of soft, shitty soil, just put the cable in cast iron shells and let it sink. If it gets hit by an anchor, then it gets hit by an anchor. Are we missing a trick here?
Well, yeah, I mean, I guess it depends on the ultimate consequence, right, of what happens if that cable gets hit. You could argue that an entire wind farm being knocked out and not producing power for however many months it was to take to repair it, that's a pretty high consequence. So, yeah. Yeah, it's all about what level of risk you're comfortable with. And I mean, ultimately as well, I mean, I'm not a legal person, but I would suggest that if you said to your legal team, no, we're not going to bury this thing, we're just going to leave it on the seabed and encase it in things, they would have quite a lot to say about that, and insurance wouldn't probably be super happy. But no, it's an interesting thought. I mean, this is what we mean by remedial work. You know, it's not just rock dump. It can be concrete mattresses. It can be these additional protection systems. But yeah, it would ultimately come down to a cost benefit analysis as well, right? So if it's cheaper and you say you've got really high strength clay and you think we're never going to bury this thing more than 0.1, even if we try our best, or you're on bedrock, you're not going to go and try and trench that realistically. You're going to try and think of something else but yeah, so these systems can 100% work, and in the right situations will definitely be more cost effective.
But it wasn't cheaper to put it in the half shells than to bury it, Terry. It was more expensive putting it in the half shells than burying it. But now they couldn't bury it because of the rock. So it wasn't an economic solution that made them choose the half shells.
It would come down to a cost analysis, you say, because yeah, spending.
But they had to mobilize a special machine to put the half shells on. That was quite expensive for them to build this machine to put the half shells on, and so it was a very expensive operation to get those half shells on. So it was no way competitive by a trenching operation.
We have, I think, a comment there to this, so maybe let's, yep, go ahead.
Yeah, respectfully, and I love a good debate, and I like the naughty corner too. I think it depends where you are in the world. A lot of Europe has governments that regulate burial depth, so there's a permit requirement that says you must bury. The UK is currently free of that, but I would put that down to customer choice. The customer needs to be bold and make decisions about where he wants to bury and how deep he wants to bury. And my own experience is that burial trumps all other forms of cable protection, but I've also installed systems where I've gone out and surface laid from the start, and I will cast iron protect over rock, but maybe not over sand. So it really is a case per case and what you're required to do, and having bold customers that understand the environment they're working in.
Good. Then let's take a question.
Yes, I have a question. Thank you very much for the presentation. It was very interesting. I was wondering that if the tool doesn't get the cable to the right depth and the tool is performing in the way it should be performing, you can prove that, then the issue is with the soil.
Yeah.
Soil is apparently stronger, better performing than initially thought. Yeah. Would that not also require you to do the reassess the risk involved there, and also maybe the chances of the cable being damaged by an anchor if the tool doesn't get it to depth?
Yes, that will 100% feature in it, because unfortunately when you're doing any sort of site survey, you can't just do locations across the entire route. If you've got a 48-kilometer cable route, you're not going to be doing a sample outside of probably every kilometer if you're lucky. I've seen every 2. So it is not unusual at all to come across ground conditions you're not expecting. And it can go both ways as well. I've seen cable, like plows, literally just sink as they're going along, because all of a sudden they've hit a patch that's just unbelievably soft, and there's no way of predicting that. So yes, you would probably have to reassess that area if you suddenly hit something very soft, because that suddenly now becomes a very high risk area, because suddenly your ability to protect that cable using the overburden or the material above has suddenly become negligible, because that, as you saw from that graph, soft clay is going to do nothing. So you would 100% have to probably almost take a step back and reassess that section completely from scratch and just do a targeted rock dump there. But similarly, if you suddenly come across something very hard, it can be a problem for trenching, but actually it can help you from an anchor penetration perspective, because something very hard will do a very good job of resisting anchor. So maybe you don't need to go quite as deep there. So it's all about live support and live assessment that you sort of need to do. But yeah, that's exactly the sort of thing we're talking about. Yeah.
All right, thank you.
No problem.
Perfect. But then, let's say we can say thank you once more. And we can move on into the coffee break. So we will break now and meet again 11:15. And don't forget to speak to Chas about his ideas. All right. So as the last people are pouring in, we will slowly get started. We're on to the last leg of presentations. And our next presenter is going to be Richard Hill from Waves Group. Richard.
Good morning, all. Free to go, so not long now. My name's Richard. I'm wearing two hats today. I work for Waves Group, and I'm here as a subsea cable specialist and a mechanical engineer. About the cable specialist bit, my wife calls me special a lot, generally in a row, so I'm a bit nervous about that, but that's fine. I've been involved in marine engineering since 1989, in subsea cables since 1993, so sort of 30 plus years. And I've also been a mechanical engineer through all of that. So I'll try and stay in my lane, which is mechanical engineering. But we are talking about subsea power cables, and it's multidisciplinary. So I will try not to diverge too much, but I may. So first of all, who are Waves Group? We're an independent multidisciplinary marine engineering consultancy. Bit of a mouthful. Quick focus on the word independent. We're involved with insurers, acting on behalf of the insurers and the developers. And our business is on a kind of a three-legged stool basis. We have consultancy that we do. Most of our work in offshore wind is marine warranty, and we do a lot of marine warranty survey. We've done about 3,500 kilometers of export cables and about the same of array cables. And then also we do casualty work, which is wrecks, salvage, incident
Richard,
management.
I'm very sorry. Can you please just speak to the mic because the virtual cannot hear you?
Sorry,
Thank
is
you.
that better? Thank you.
Yes, perfect.
Apologies. So to go back a little bit, we have three lines of business covering consultancy, marine warranty for energy, and then casualty management, which is instant response for wrecks, salvage, and out of that claims as well. And the link between all of those we like is data. We use a lot of data to visualize what's going on and try and find root cause of failure when things have gone wrong. So today we're going to talk about faults, and I'm going to try and break some myths. So we're going to talk a little bit about root cause of failures and compare telecom sector and power cables. And across my 30-odd years, I suppose I've worked 20-odd years in telecom and about 10 years in power. So I've got a little bit of experience of both. We're going to dive a little bit deeper into cable designs, and hopefully I can answer the question that was asked earlier. A little bit of insurance, and then some principles for improving quality and reliability of power cables. I'm going to burst a bubble now. There's no rocket science here, nothing new. I'm just going to try and go through things in small bite-sized chunks. And then a little bit of a look into the future, and there's been a lot of discussion about DSS and DAS and fiber optic sensing. So I'm going to try and have a little bit of a look forward, how it might be helpful. And then hopefully there'll be time at the end for some questions, but we'll see how we go. So first myth, submarine cables are not 100% reliable. The global fiber network is, well, in excess of 1.7 million. I know one of the suppliers has announced this week it's done over 1 million. Another one that was here today has said it yesterday, 800,000. So we've put a lot of kilometers in. And globally, there's a fault across the network somewhere between 150 and 200 a year, which works out about once every 2 days. So they're not 100% reliable. You need to build that into your thinking. The power network is a lot smaller on that global footprint, and trying to find accurate numbers is hard, but a little bit of search on ChatGPT, and I'm estimating something like 50,000 kilometers globally at the moment. I'm welcome to take firm numbers if anyone does know. But it also predicts to grow to about 125,000 kilometers by 2030. So we're in this huge boom at the moment. We're all riding a big wave of installation. But the fault data is commercially sensitive. And there's a lot of good reasons for that, but it doesn't help us really focus in on what things we should be working on. So I'm going to hopefully pick out various points as we go through that have already been talked about today, but maybe with a slightly different spin on them. We'll see. And when I was in my AI search, I also asked it how many faults there are per year across that power network. And I got an answer of something between 20 and 25. And I feel that's probably about right with what we're seeing. But then it also said it's growing to 300 faults a year by 2035. And I found that a little bit scary. And I wonder if that might be ChatGPT having its own little wobble. So rubbish in, rubbish out, we talked about the other day. I don't know if I believe that. But if it's true, it's quite a scary number. So what do we know from telecoms? So this is data that's been collected since about 1959 when the ICPC started. They've got a really comprehensive database across that few million kilometers. And the overriding message is that 80% of faults are estimated to be caused by external aggression. So that's fishing, anchoring, dredging, geological activity, those sorts of things. There is some unknown in there as well, but that's looking at the whole global network. So we're into Asia and the Pacific. But the component failure, which is how telecoms classifies the internal issues, is down at around 5.9%. So quite low. If we look at the information Catapult collected, and this is just based on UK offshore wind and just HVAC cables, they're estimating about 8% are caused by external aggression. So if my simple maths is right, that's about 92% of faults caused by cable design, manufacturing, and installation issues, which again is quite concerning. But rather than go down the doom, I think there's good news there, because all these things are under our control, so they're preventable. So I never like to go to a party empty-handed, so I've gone through some of our database. Wave has been supporting cable repairs for about 15 plus years. We work across telecoms and power, but the telecom sector work we do is generally in damage claims. But for the renewable sector, we work across the full spectrum of failures, and that's in our role as MWS. And commercial confidentiality comes up quite often. I hope not to transgress any lines, and we don't always hear the root cause of failure, but we'll try and dig in a little bit to what we have got. So the first one, the graph you can see, it just shows that the trend shows there's an increasing number of power cable repairs that we're involved with. That may well be expected as the number of installed kilometers increases, so you can say that's a logical next step. It could also be that we're being more successful at winning work in that area as well. So there's greyness around all these things. But as we dig into it a little bit, I asked myself two questions of the data. The first one was, what cable type is causing the biggest problem? So I looked at, is it an interconnector, an export cable, or an inter-array cable? And then picking up on this preventable issues, is it a cable failure due to design, manufacturing, installation, or maybe another internal issue? And then there's always an unknown section. We don't get to see everything. So looking at the cable type first, the pie chart on the left, approximately 60% is inter-array cables by volume, and then about 20% on export cables and about 20% on interconnectors. So there's a broad spread, but I would say the CPS issues has had an effect on those numbers over the last few years. So, you know, it's a noticeable thing. And then we go into the root cause of failure. And on the jobs we've been involved with, over 70% fall into this category of preventable issues, and only about 20% is external aggression. So trying to be positive about this, there's a lot of work to be done to help improve the reliability. So a little bit of a talk about cable design. It's complex due to the variations in design. And if we start with the telecoms cable on the left, they are a highly engineered product. I've got one here. It's not very big. That's what's lying at the bottom of the Atlantic or the Pacific with the internet in it. But it's an incredibly robust structure. And there was a question earlier about fiber optic cables being crushed and their sensitivity. Well, this is rated to 3,500 meters. That's 350 bar pressure, unbelievably resilient to crush. But when I look at some of the fiber optic cables that are being installed, I see they're missing some of the key elements. And if you can look at the photo on the right here, basically it's got a central tube and the fibers sit within that. And then there's some strand wires around the outside. And this product is really a wire rope with the fiber in the middle. And the strand wires are configured so they are in a vaulted structure. So it's remarkably strong in tension, remarkably strong in compression. And the design brief the telecoms started off with back in the late 80s was they wanted to be able to install and repair this cable 80% of the time anywhere in the world. So they designed the ships and the cable to be operable in abyssal plane depth, 3,500 meters of water, sea state 6, which is quite a challenging marine environment. And most of the wind farms won't go there because of the cables. So if we now move on to HVDC, and where's the plinger? I'm going to introduce another word here. The HVDC cores are also coaxial. They're all concentric around the central core of the cable. But the HVDCs are getting a lot bigger. So here we're now talking 125 to 200 mil, 25 to 50 kilos a meter. It's a lot bigger, a lot heavier construction. And generally in HVDC, they're installed in a bundle configuration. And that starts to complicate things, as we've heard earlier. The middle diagram shows a 3-cable bundle, but the industry is moving forward. We're now into 4 cable bundles. So they're taking the metallic return path out of the poles and making that as a separate cable. So all of this increases the complexity. What's shown there is a bundled cable. There's lots of variations on that. There can be tight bundles, loose bundles, no bundling, but laid through a tool in a bundle configuration. But it just complicates things. And a number of people have talked about all the cables need to be able to move relative to each other, and this is key. So I've deliberately shown this in a vertical configuration. Some are installed horizontally, some are installed vertically, but I think you can all visualize if you're going around a bend in a vertical configuration, the cables at the bottom either need to be moving faster than the ones on the inside, or they're going to see more share of the load. So it's quite key. And then we move on to HVAC, and I've put this last because I think these are the most complex mechanically. I've got a bit of a core here as well somewhere, just to get a feeling for the size. This is a baby HVAC core, a 240 mil copper, but we've got 3 of these in a helical construction, so wound in a helix, in a trefoil construction. And as a mechanical engineer, I think of that as 3 springs interwound. So it's a lot more complicated than the coaxial constructions we've got. And that's also got various elements in the interstices, in the voids between. You might have fiber optic cables and all sorts of other fillers. So it becomes a really complex structure. And then you've also got the armor wires around the outside. And the load is not carried by all the armor, and the load is not carried by all the cores. The loads are shared between these elements, and that's key. And that's from the mechanical perspective. I just wanted to touch a little bit on the electrical. I'm not an electrical engineer, so if there are in the room and I get it wrong, please help me out. But EMF and dielectric stress is really key. And there are lots of layers in each of these cores, and they all have a purpose. And some of those cores are the screens, and their job is to keep the electric field concentric, the dielectric stress is concentric in the insulation, and that's key as well. So there's lots going on, so it is complex. So in summary, yeah, subsea cable designs have lots of similar characteristics, but their configurations may be different, and they're installed in their own unique environment, and each environment is dynamic. So, insurance markets insights, we heard a lot about that yesterday. Some of the numbers are eye-watering, 83% by value, the total share of claim costs, I think is quite shocking. And what does that mean to the insurance market? Well, in 2020, it was 585 million. That's in the public domain. I can only think that number is bigger now. I don't know if anyone knows any numbers, but it's quite eye-watering. And I was taught that insurance is for the unforeseen, not for the foreseeable. So that means if we can see there's an issue, we should be engineering it out. And then the insurance is there to carry the things that we haven't been able to engineer out. It shouldn't really be there to cover things that should be engineered out front end. So, cable engineering. It's a multidisciplinary activity. And Chris was talking about getting more people. Please, can we have more cable engineers? The industry is booming. Cable engineers are key to that. And cable engineering is complex. It needs to match electrical, mechanical, thermal, and optical requirements with the physical requirements and nature of the route. And I'm going to put permitting in there as well, which is another curveball, and the installation techniques and equipment being used. Good cable engineering is iterative, and it's a process. And we've seen that hopefully through this morning's. And you have to bring these things together to ensure cable integrity is maintained. And that takes time and expertise and communication across that multidisciplinary team. And if that process isn't followed comprehensively, then unfortunately, we are going to see faults. So good cable engineering requires that multidisciplinary approach. Now I'm going to talk a little bit about mechanical handling, and I see time's running quickly. Relatively minor cable malhandling can significantly change the internal mechanical and electrical stresses. And the best explanation I've received is that power cables can bruise. You could say power cables have feelings too, but I've focused on HVAC. It's really important that those three cores can move relative to each other, or you can't go round a bend, as Hendrik was explaining earlier. And if one of those cores gets trapped, its share of the load increases. And so I've seen quite a few HVACs taken apart where the cores are being compressed and you're getting flats where the three cores are coming together. So that's changing the shape of the screen. So that's changing the shape of the dielectric stress and introducing increased accelerated aging of the XLPE, which is not good. And then you may also be bringing in some sort of mechanical crack into that. It's not uncommon to find cracks in the lead sheaths, and that may well be a micro crack at initiation. But when you think about that cable through life, it's almost a living thing, expanding and contracting as the thermal loads are increasing and decreasing. So that propagates into a fracture, lets in seawater. So if you get one or more of these things happening, you have a perfect storm of cable failure, really. Industry is aware. I've got lots of organizations, organizations are doing their own thing. SEGRA is got a working group looking at testing. DMV standards exist. They've got lots of good information. ESCA's recently introduced the mechanical handling guideline. I know there's mixed views on it, but I'm going to talk about one element of it, and that's critical cable handling parameters, bit of a mouthful, or CCHP. each cable's critical limiting parameters must be adhered to, and the cable must be operated within those to maintain good cable integrity. That's really key. And that has to be applied along with the standards to specific cables and their vessels and the equipment combinations, because you have to determine the boundaries of the working conditions on the site, and that changes. So please, if you get a chance to download this, do. It's available through, I think you have to email the chairman, but it also talks about lots of important things. It's got definitions for cable integrity, sidewall pressure, squeeze load limit, tensile force distribution. These are all great things that I think we need to socialize more. So MWS, from our perspective, thank you, Mike, for talking about JNRC. I'm going to talk, well, I'm not going to talk you through it, but DNV STNW1 is the MWS DNV standard we work to, and it's really hot on monitoring equipment and installation monitoring. There should be nowhere to hide. And good record keeping is critical. So following a fault, everyone wants to know why the fault occurred and who is liable. And proper cost allocation can only be achieved if you've got that evidentiary set of records. And under DNV, no warranted marine operation should proceed unless that data is being logged. So where is it, and is that making its way through the process? These records really are critical in the event of a failure, and they may not provide you a smoking gun, but all the ones I've found, there's always provided really good information and insight. So I know I'm running out of time. Fiber optic sensing, thank you, Dan and Etienne, for their descriptions of DTS, DAS, DSS, and others. For me, the magic comes when you use these things together and over a period of time, and they offer fantastic capability. My introduction to them was back in 2014. We were doing some fault pinpointing, and we were struggling with the electrical techniques. The area of uncertainty was too great to define a cut position. So the particular cable we had it was an early variant of G652, so it wasn't hydrogen resistant. So we were seeing hydrogen darkening in the fiber along with a hotspot on the cable, but we still didn't know where it was geographically. Where were we going to cut? So we ended up driving the ship up and down and feeling the ship's props and lining that up with a hotspot, and we were bang on the fault and knew exactly where to cut. So bringing all these things together is really, really useful. And it's great to see an increasing awareness of this across the sector, and it's an important and developing technology. And where might it be in a few years' time? I would love it to see it covering the catenary from the tank through the cable engines and whatever chutes are on the back of the ship, through the water column, and maybe through the burial tool. There's no reason technically why it couldn't be engineered so you can actually feel what the cable is experiencing, which would be a great step change to make that data available and transparent. And then also into floating wind, a lot of people have talked about that. Why not monitor and count the dynamic cycles the cable's going through? I believe that's certainly possible. I see I'm running over, so quick summary. Look after your cables and they'll look after you. Good cable engineering is multidisciplinary. And if there's one takeaway, know your cable, they're all different, and understand your cable's critical cable handling parameters, the limitations of the environment, and the installation spread and the equipment. It's all interrelated and dynamic. Monitor, measure, record, and keep those records. You probably will need them in the future. And then develop, specify, and require the use of new technology. And the last one to me is the golden nugget. Let's learn the lessons. Let's feed these lessons into the future by writing them into the new technical specs and writing them into the contracts, because putting them into the mix after the contract's been signed is too late. they need to be in the whole contract at the front end. So that's me. Sorry, I've run over a little bit. Thank you.
Okay, but then let's take one question from the audience. We have one over here.
Hi, Richard. Thanks. That was a great presentation. I'm just wondering, from your experience of as a marine warranty surveyor and reviewing maybe root cause analysis for faults, do you think that is it ever investigated the site acceptance testing or the factory acceptance testing that goes into like following manufacturing and also installation? Because from an operator's perspective, we think that the testing isn't sufficient enough at a site acceptance level because the equipment isn't available to be able to test on offshore environments. Do you think if the testing was better and there was more of a standard for it, we'd be able to kind of highlight these issues?
Short answer, yes, absolutely. I'm now answer that hat as the marine warranty surveyor, which is the question you asked. Our scope is very clearly defined in JNRC, so we have to operate within that scope. If we're asked those questions, we can do maybe side work outside of the scope on a consultancy basis that can address those things, but we're constrained as an MWS about what we can look at and how we can look at it. So we're really there on behalf of the cable, and is the operation that's presented to us working within the standards. So that's how we look at it. But absolutely, I fully believe learning the lessons, testing, FATs, all of it, it's the whole process that needs to be worked on and improved, and feeding it in front end, so that's part of the requirement, is key.
Thanks.
Right.
Cheers.
You have a follow-up question?
Oh, I was just going to say thank you.
Yeah, perfect. Good. But then, thank you very much, and we'll move on. Thank you. Good. Then our next speaker is Sean Kelly from Transmission Excellence.
Okay, let's try this. Right, so the obligatory bit about who's Transmission Excellence, TX. This is where we're based. Looks very English. We're a provider of consultancy and software, and where my clients are. Software products we have is three you see there. The one on the left is for grid operators like Nesso in Britain. We're not going to be talking about that. The other two, TX Array lays out the array cables within wind farms. TX Dynamic looks at the ratings of export cables for offshore wind. And I will be talking about that with a particular angle being cable reliability and economics, the particular spin for today. Move on, a bit about me, background, electrical engineer originally. Worked in National Grid for many years, ended up as the project director for BritNed. I think yesterday there was a story about a cable that had been hit several times by a Dutch trawler. I think that was BritNed. Then went to Transmission Capital, one of these off-toes people were cursing yesterday. They're really wonderful things. They're not cursed at all. And I was technical director there for 7 years, and then set up TX. And cable reliability, as I said, reliability and economics are going to be some of the spin today. So talk a bit about cable reliability. If you were here yesterday, there was doom and gloom session in the afternoon about how terrible everything was. And maybe you think I'm going to come in and tell you, no, it's okay. No, probably not. This is a bit more the doom and gloom. Okay, cable reliability source data. I think someone did mention about the Seagray. Yes, I see it's kind of more electrical equipment reliability information. They tend to be the gold standard. There's this 2020 report, I think was mentioned yesterday. There's a more recent 2024 update to that as well. And looking in those is for AC. They've got data about DC as well. Looking in there, one thing of note, I would say, 500-year mean time between failure. Oh, no, 3,000-year mean time between failure. This is for if you had a 1 kilometer length of cable, how long on average could you go before it breaks or something hits it or whatever other failure occurs. So big range there. That's one problem. Second problem, the amount of operational experience it's based on. You'll see, particularly for the older one at the top, 4,000 kilometer years. That's not a lot. Bit better for the later one, it's 17,000. So first thing, big range. Second thing, not based on a huge population. Third thing, it's anonymized, of course, but that kind of makes it less useful. What were these faults? Was it all one terrible cable in Japan somewhere that biased the whole thing? Do we know? So because it's anonymized like this, there's a limit to how much information you can get out of this. So an alternative, okay, Britain, offshore wind farms, export cables, high voltage export cables. There's a lot of them. You see, it's gone to nearly 3,500 kilometers now in service. And if you look at kilometer years of operational experience, it's actually, what's that, 25,000 nearly kilometer years of operational experience, which is actually bigger than the Seagrey data set. There was one with 17,000, one with 4,000. This is nearly 25,000. So it's actually bigger experience base than the Seagrey data set. And if we look at that, another thing is that projects or faults that occur are, particularly if they occur after transfer to the OFTO, faults are made public. Not always made public straight away, but within a year usually they're made public. And there's usually some information about what the fault was, as well as just the fact that it occurred and how long it took to repair. So what we're seeing at the moment, so far out of this data set, we've seen 18 faults, and I'll say a little bit later how I define a fault. I will just come back to that later. And a 24,000 years, so it's 1,300 year mean time between failures. It's kind of between the Seagrey's high end number and Seagrey's low end number, so it's kind of in between, which is reassuring. And then we've got this 24,000 kilometer years of operation. How's that split out between individual wind farm projects? This is, you'll see the newest ones on the right is a very small number. That's not because they're very short cables, just because they've only just a couple of months of service. They're not adding up the kilometer years yet. And then, so which of those have had faults? Is it the longest? Is it sort of randomly distributed? It's not random, is it? There's one project in particular seems to have more than its fair share. Anyone want to guess which project that is? Of course, Quinty Moore. I remember one of the conferences calling it the cursed cable, and I never heard the end of that one. But yeah, it's had more than its fair share, for sure. And a little small print there, just say this is only UK projects, this is only wind projects, wind export cables, 132 kV or higher, so 132 kV or 150 or 220 kV. Only requires repairs that require mobilization of a cable vessel. So not including terminations offshore or terminations onshore or transition joints or anything like that. This actually has to be a vessel mobilized to go out and do the repair before it appears on that. There'd be a good deal more if you were including other failures. And finally, it is only looking at the operational period. What operational means is a bit variable, but certainly the construction vessels have left site by this point. So failures like the infamous London Array failure where a jackup jacked itself up on top of an export cable and broke it isn't included in this, for instance. That's a construction stage failure. These are operational stage failures. So I guess anything that's construction all risks insurance is responding, that should be excluded. This is operational failures. Okay, so there's been a reasonable amount of failures. Not randomly distributed, but the bad news is I don't think there was anything on Quinty Moore before these failures started occurring that would have led you to believe it was going to be bad. So there's no way to say my project will be different because I can see I've done this bit. Nothing particularly wrong with the cable apparent at the time. I don't think you can make that assumption, try and exclude it from the calculations. Cable repairs. So I thought this would impress people, but I'd see how expensive these cable repairs are. And I got blown out of the water by this one in Taiwan that I found out about yesterday, where it was 25 million just to get to Taiwan before they even started a repair. But on most repairs these days are on the order of 20 million pounds probably for a repair, 15 to 25, but let's say 20 million pounds. Repair time. This is some survey I did back in 2017. Average came out was 4.2 months. It's broadly comparable to 3.1 value in, there should be the word C grey there, somehow fallen off the presentation. So 3.5, 4.2, yeah. How is that getting on? That's since 2017, that's 8 years ago. Has it got better? Has it got worse? Well, here's the last 4 repairs in UK offshore wind. 5, 6, 8.5, 6. Average is 6.4. It's getting worse. Of what we were hearing yesterday about, S-Link 2 and so on, it's not, it's not going to be better than these statistics. Actually continuing to get worse. So reliability is a big deal. It is important. It is a problem. What we're going to do about it? Well, let me talk about this TX-Array software that we have. And one of the things it does, well actually, next slide, what it does, it minimizes all of these cost elements. So the cost of building it, all the little elements at the top. Cost of energy losses in the cables has been in the middle. But the bit I'm going to focus on, the bit at the bottom there, the energy that the money you never make, the loss you make because your wind was there, the wind turbine was ready, but it couldn't generate because it had been disconnected because the cable had failed or some other failure prevented it from generating as much as it should have. We're going to focus on that bit. So, and this is just a bit of further information. It's a wonderful optimizer because, and it saves. This is compared to as-built designs to up to 12% cost saving on the array cables. And what can we do with the array cable design to help with reliability? We just found reliability is this big problem. How can it help? So here's an example. The top design, you've got your cables turbines cabled up one to the next to the next. And on the bottom then, we arrange them in 2 separate sub strings and then combine into a single string and then goes into the offshore substation. And it looks on this like the tree design has much longer cables. That's just the way I've drawn it there. In reality, the cables can actually be shorter with a tree design. Just depends on how the turbines are laid out. And compare that. So with your linear string, you can see if you get a fault at in the leftmost position, you can be knocking out 5 turbines in one go, and then the next position is 4 turbines in one go, and so on. And with a tree design below, you can't actually knock out more than 3 turbines with any failure. And you do the sums, and turns out with a linear string design, there's 3 turbines on average lost by any random fault, and with a tree design, it's 1.8. So there's an example of how you can improve reliability. And this is one of the things that in doing the design that TX-Array automatically takes these things into account, turns them into a monetary value based on reliability assumptions, mean time to failure, and mean time to repair, and cost of energy, works all those out into a monetary value and optimizes it. Okay, this is about switchgear. I'm not going to talk about this. Anyone wants to talk to me about this, ask me over lunch. Okay, loops. Here's another way of improving reliability. There's typical loop design. You got 2 strings, and then there's a dashed line represents another array cable that is not normally in service, connecting to 2 of them. But if you have a fault, you energize that not normally in service cable, and then all your turbines now have a route back to the substation. One point about loops, I find people not always clear on this. So in some cases, if you have a fault on the cable, you'll be able to have all your turbines still working. But I've never seen a case, and TX-Array has never suggested a case even, where you would have, in any circumstance, with any cable out of service, no matter how windy it is, all your turbines will be able to generate. No, that's never the case. There's always some limitation. It's never economic to give maximum output in all wind conditions under any fault condition. But it will help you, certainly. There's an economic benefit in that in many wind conditions, you'll be able to get most of your power out in most fault conditions. Also significant, you keep auxiliary power supplies to all those turbines, and you keep a fiber connection to all those turbines and comms link to all those turbines. This is a study I did for a client a couple of years ago. We looked at loops and a conventional tree design. And the end, sort of the bottom line there, to justify loops, you would need to be willing to pay £6,000 per turbine per year for have a guarantee that you would have a connection back to the substation for auxiliary power, and a guarantee that you would have a fiber optic connection to your turbine for control and monitoring. And interestingly, what happened was the client was like, "Oh, that's great. That's a brilliant idea. Yeah, I'm going to do that. 6,000 is not that much. It's worth it." Write a paper to the project director to get that approved. And the project director came back and said, "Not taking that out of my budget. I don't care if it's going to save some money for the operator." So it never actually happened in the end. But in principle, that's a way of improving reliability. Here's interesting. Different countries have different favorite architectures. So Germany loves loops. Here in the Netherlands, linear strings are the way to go. If you're in Denmark or Britain, it's kind of a mix. And I think that's because things like loops, the economics are kind of on the edge, and you can kind of justify doing it one way or justify doing it the other way. And because that, a lot of people just, well, what does the guy next door do? You know, what does the previous project look like? I'll copy that. That's interesting. It's sociology, not engineering, that determines that design. Okay, moving on. Cable rating. So, and I thought there was going to be an economic spin on this. So what cable rating is about, there's a picture of a 3-core cable. Power flows through it. Not all the power gets to the other end. Some of it is lost in the conductors, which are sort of orangey, yellowy, or the sheath is the blue bit, or a bit in the armor as well. That red stuff is the heat coming out, eventually flows into the sea. Because that heat has to need a thermal gradient for the heat to flow, so the heat's up inside. The more power that goes through it, the more heat that's generated. The more heat that's generated, the hotter it gets inside. That sets a limit on how much power can flow. It's something called continuous rating. That's the amount of power you can put down it non-stop. And if you do that, the temperature will get to 90 centigrade, which is the maximum allowed, and not go any higher. So that's what continuous rating is. There's this thing called dynamic rating, which is used by probably most wind farms, the most AC connected wind farms these days. And the idea there is you're allowing the turbine, or more megawatts of turbines than there is capacity on the export cable, continuous capacity on the export cable. And how you get that, 3 things. One, the cables heat up slowly and the wind doesn't last forever. But that dashed line shows how the temperature would have gone up if the wind had stayed blowing forever, but it didn't. If you see this actual DTS temperature measurement, it rose and then fell down again because the wind stopped blowing. Secondly, not all people include this. Ambient temperature varies, and it's lowest in the winter when the wind output is highest. An extra little bit you can get out. Some clients have found that quite useful. Not all the turbines run all the time. You'd be, say, 100 turbines in a wind farm, you'd be pretty unusual to have every single turbine operating at the same time. Then it's dynamic software that we have. Takes an economic approach. So it's not looking to say, I want to make sure, calculate this dynamic rating so that nothing can ever overheat, given some assumptions, because the assumption is just an estimate. I want to make sure nothing ever overheats. Rather, the economic approach is, I want to maximize my profits. Let's start from there. And what do we mean by maximize profits? Well, here's our idea. So the cost is on the vertical axis, and on the horizontal axis is how much extra rating are you getting from your dynamic rating. And if you don't use dynamic rating enough, or not at all, you've got this expensive cable, and you're not putting as much power down as you could have. So pounds per megawatt hour, euros per megawatt hour is high because the megawatt hours is lower than it could be, so less profit. If you go to the other extreme, if your dynamic rating is too far up, though, you end up with generation runs, the temperature of the cable goes up, hits its maximum allowed level, and you have to turn down the wind turbines. You put all these extra wind turbines in, they can't get the power out. Again, you're going to lose money. And in the middle is your ideal place. You want to find where that is. Within sort of the core, if you like, of the TX Dynamic software is this thermal simulation. This runs over 50 years. There's this thermal simulation, a temperature simulates the temperatures inside each component within the cable and layers of soil and so on. And you can see there over 50 years, the blue at the top is the conductor temperature, which you don't want to go above 90. And you can see it's going up and down in that zoom in. But over 50 years, there's this blur of blue because it's going up and down so much. And this is with no curtailment. If you put another 10% power down the thing, you would see there it's hitting the 90-degree limit or just below the 90-degree limit, and it's kind of flattening out. Where the temperature is flat like that, it means somebody is turning down a wind turbine somewhere and money is being lost somewhere. So you want to measure that, how much money is being lost, put that into your economic calculation. I won't go into detail. As you can see, there's the thermal simulation, there's electrical parts, there's economic part. I won't go through the details of this. You can ask me later if you want. But what happens here, basically, you can do it two ways, right? You can change the size of the cable, or you can change the size of the wind farm and find out, in this case, saying we'll fix the size of the cable, we'll change the size of the wind farm. That's on the left-hand side, change the size of the wind farm. On the right-hand side, the economic impact of having to turn down the cables, turn down the turbines comes out. Putting these together, this is sort of actual results from a few years ago. And you can see what's happening. There's an optimum there where the costs are minimized. So this is cost on the vertical axis. The cost minimized equals profit maximized. The most profitable bit is about 120% extra dynamic rating. So if you had a 400 megawatt, 500 megawatt cable rating continuously, you'd be putting 600 megawatts of wind turbines on it. And you can see that is saving 10%, which back then was about £1 per megawatt hour, which is a significant amount of money. I mean, it's probably with the inflation since then, it's probably about £1.50 now. So it's a pretty significant amount of money that you can save from this, and that's part of the economic twist on this. I think that's my last slide. Let me just right. Okay.
Thank you.
Thank you very much.
So, do we have questions? No, then I'll raise one of my own.
Okay.
Yeah. Or do we? No. Then you showed the architectures or the different types of architecture, and you also mentioned that the step to 132 kV will significantly change the cost per wind turbine. Do you expect the architectures to change significantly going forward, or are those the choices we have?
So I think, as you say, the change to 132 kV helps loop designs because there are the cross piece between the two substrings is now a smaller proportion of the total. So that change to 132 kV would help loops. Also, as time goes by, turbines seem to be becoming more sensitive to loss of auxiliary supply. So even some of the latest generations, sometimes you see them with built-in diesels, for instance. I've seen in some projects. So I think that again would contribute to a preference for loop type designs. On the other hand, we're seeing more people getting interested in putting batteries in. So you can say, well, there's a battery there. Why am I so worried about my auxiliary supply? I've got a battery instead. So it's hard to say how it's going to there's these conflicting trends. But I think, and the other factor as well, I should mention that's significant is how many export cables you have. Because I've seen some projects, for instance, that they've only got one export cable, and it's a DC export cable. That would tend to be the converter reliability issue on top of everything else. And if you've only got one export cable, why would you bother putting loops in? Because you're going to be exposed to losing your auxiliary supply anyway. So think, well, I'll put a battery in. Why would I put loops in? So that also has an impact on it. So it's going to be a different assessment in the future. I think it's still probably going to be quite a narrow assessment. We may still see the sort of sociological factors of what's our previous project look like? What's the project next door look like? That's probably still going to drive things.
So you don't see us building meshed array systems? It's going to be loops at best.
We haven't really seen them to date. I mean, Triton Knoll probably came closest. If you are a lover of the sort of Siemens OTM approach, where I got lots of little substations, they can go well with those. I haven't chosen to go into that in this presentation, though. I think I've just used my time anyway. So,
good. Any other questions? No, I can keep going. If there's something you want to know, you ask. Otherwise, no. But then another question I had was on the dynamic rating. You showed that we could basically use 20% more of the cable. Is that supported with real-time monitoring or based on a static assumption that the wind will never blow hard enough, long enough, and then 5 years from now it will happen, the once in a millennium wind?
Yeah, you will really, it's really important to have good DTS support to make sure that, I mean, even if you use the continuous rating, I think you still have DTS because are you absolutely sure the thermal resistivity of the soil is what what your survey said? Surveys are not very good at measuring things like that. Are you sure your cable burial is what you expected? We've had things like the Oslo Fjord, 10, 15 years ago, Oslo Fjord cables which burnt out because they were designed to be surface laid, but they weren't surface laid. They actually buried over time. So even if using continuous rating, there's risk. So you need to make sure there's DTS. If you're using, making use of the dynamic ratings, it's even more so, I would say. I think we'd recommend, probably you have 2 independent DTS systems. I'm not sure many people do that, but that would be our recommend. We did some work for Offshore Wind Accelerator on this a few years ago. We did recommend that. We would recommend people would have a margin of safety. So I think in the picture I showed you, it wasn't 90 centigrade, it was 88 centigrade. Because remember, the DTS doesn't actually measure the temperature in the hottest part of the cable. It measures the temperature between the cores, not inside the core. And then some calculations will convert that into what the temperature it thinks it is in the core. But there's inaccuracies in the DTS measurement. There's more inaccuracies converting that into the computed temperature in the core. So you want to leave a margin there. And I know some people I've spoken to, some large developers said, well, don't worry about this. The cable is actually tested by the manufacturer at 95 centigrade. There was a lot of pushback from the manufacturers on that. And I'm with the manufacturers on this. That extra 5 centigrade is the manufacturer's safety margin. It's not the user's safety margin. And I do agree on that.
So do I, because if it fails, it's going to be a manufacturing issue that caused it and not the overheating. Good. Okay. But then, thank you very much.
Thank you.
So we are on to our final presentation, and that's going to be Jürgen Zeilmans from OSPIT NL.
Well, good morning. My name is Jürgen Zeilmans from OSPIT, and this morning I would like to talk and give you an introduction about the company and what we do. OSPIT is a company based in the UK, headquartered in the UK, 200 people. Since 2 years, we're also based in the Netherlands, here close by in Rotterdam. And what we do is we design and build bespoke equipment. Our clients are the subcontractors, the contractors and the developers. Pretty special is that we design it, build it, and building is setting up a site that is convenient and go there with the team to actually deliver from a local place which is convenient for the project in terms of cost or mobilization. We have been involved for like 15 years. The first projects were actually offshore wind. We were sidetracked a little bit in oil and gas, but pretty much in offshore wind, like 95% of the projects. And every time I present, I sit at home making the presentation, preparing the slides, and my 2-year-old and my 7-year-old son come look what I'm doing. I had a big shark, so my 2-year-old, I looked at him and he started making this blobbing noise, and I was like, yeah, it's a big fish. So he's pretty spot on. My 7-year-old said, what are you doing? I mean, what are you involved in? Why are you doing this? Why is there a shark? And I think to summarize the past 2 days, the whole cable repair and failure bit of the industry is a bit like a black hole. And we're not really talking about it. And I explained to him, when you look outside offshore, there's a lot of wind turbines being installed the past 15 years. And we intend to install, to double that figure the next 5 years. So there's a huge challenge ahead. Just listening to all the failures that are around, and we're not really talking about it, but we do. There's a lot of work potentially out there for the next 5 years. And to showcase that further, there's been some events in Holland on defense and what's happening. I think the big shark is actually there. It's the big elephant in the room. It might be a metal shark, might be a state actor. I don't know, but that's just increasing the figures on the amount of repairs coming towards us in the industry. Major challenge, I think there's too little people, but also too little vessels and equipment to do the works. And the main assets out there are basically the big boys with the big cable layers, also doing the side jobs, doing the repairs. And this case is really about a smaller player, I think, although they're rapidly growing. In 23, we came into touch with NC, and they had a brilliant idea to make a more dedicated spread. And they really didn't know what it would look like, and this is how it ended up. But that was in the summer of 23. And we started discussing doing a feed study for NC. And we provided a proposal. The main design requirements was really to have 2 independent baskets that can turn independently. It should go on a vessel, no clue which vessel. And that was it. Oh, yeah, and the 400 tons capacity, that was the requirement. So based on that, we started working on the feed study proposal, had a bit of a conceptual image. And after the feed study, we were kindly asked to participate in a commercial bidding with other companies, pretty much involved. So we actually won the bid. Not a real surprise, to be honest. And then the big challenge was to convert that idea in 31 weeks to reality. And just a few minutes ago, I heard about the response time to a failure being like 9 months, 7 months. We actually built the kit in like slightly more than half a year. And I'm pretty sure that NC can actually respond to the failures pretty quick. So I'm a bit puzzled where by the time goes with the actual failures. But there's huge potential to speed it up, looking at the complete chain of actions, let's say, when we actually see a failure happening. But that's a bit of a sidetrack for me. We focus on equipment. So the key thing about the feed study, and it was a perfect picture according to the book, we started in Holland, started up the operations. The intent was to do a feed design and then hand over to the UK to do the actual design of the system and build it. During the feed process, I started thinking about the scenario of building in Holland because the supply chain is incredible, honestly. And that idea was shaped further. UK pretty limited in capacity at that moment, and we basically dragged it to Holland. Being close to NC, that helps. We all speak the same Dutch language. What is key in this feed studies is that you actually have the specialists around the table. So on our side, the people that have the experience in the field, they know the cable equipment from the past, let's say. And it's really important to have a partner in this on the NC side with the operational people that can provide the right input, but also have the right IDs. Looking at the operational requirements, mentioning a range of cable configurations, that is like over 100 cables. Narrowing that down to a single spec for a design of a equipment is a big process, let's say. You need to do that really together. Eventually, the equipment needed to be very flexible to be able to mobilize it from different types of vessels, ranging from a flat barge to a more vessel-shaped object. That was really the unknown part, and we actually, through the project, discovered that NC actually acquired the vessel, and that became more clear, let's say. So a short movie to illustrate the process of the build. And this was in Rotterdam. So in the process of 31 weeks, we designed the actual carousel and loading tower. And this is the yard of our subcontractor. And we sent the design team to that location to guide the subcontractor to actually fabricate the steel parts. So here you see the basket getting shape. And in parallel, we built the drive system, and that's a different thing, and I will elaborate on that. So, blue color. comes out of the shed, and this was just a matter of hours, but we speed up the video to show the ID. That's the drive up going under the main carousel bit. And after this part, we installed the inner partition because it's 2 baskets concentrically. Do the full testing in the shed to make sure it's all working. And that's the loading tower parts being assembled as well. You think it's all big until the shear leg comes and picks it up. And because in parallel, NC was converting the vessel, Kuro, we were able to ship it directly to the yard where it was lifted on the vessel. And after that, we did the final commissioning and testing. And basically, the vessel went out straight away on the first job. This is the actual team delivering it. Pretty compact team to just make it happen. So going back a few steps, how did we actually get there and what's the main principles behind it? Osbit, UK-based company, we pride ourselves in terms of that we rely on the Victorian engineering styles. And that originates like 150 years back, steam-powered carousel. I think back then our carousel would have looked like that. The core principle is that we rely on simple mechanical systems and we try to simplify them and not complicate them. If you look at the industry and the carousels that have been delivered the past years or the past decade even, there's a large variety in constructions and how the actual floors are supported on the vessel with the rollers. The most simple approach with fixed rollers causes a lot of issues because, as you might know, a vessel is constantly moving. So if you go out in the morning to a vessel, you measure the deck, you go back in the afternoon and the sun is shining, you can measure like centimeters of difference in the deck. That means if you have a large surface with rollers, and that's changing all the time, the floor needs to be pretty compliant to be actually supported by the rollers. Industry found a bit of a middle ground by using, let's say, hybrid solutions, having PU roller blocks, PU supported roller blocks to provide the flexibility. It's a bit of middle ground. There's a lot of carousels out there. We also hear a lot of pops and bangs, as some contractors say. So the friction of the wheels changes all the time. Very unpredictable behavior. And we tried to get our head around it. We ended up with a slew bearing on the inside and wheels on the outside during the feed study. But driven by the schedule and the availability of bigger slew bearings from a key supplier, we decided to go all in. And that means that we went for the solution of having slew bearings. So there's a big one for the outer partition and a smaller one for the inner partition. It's fully supported by these bearings. And that makes a huge difference for us because we don't have to define the loads for a wheel system that eventually is different to what we designed for. It's very predictable what happens in the bearings. The basket has been designed in a different way, so the actual floor and the walls are sharing the load. That was also a bit of a process where we involved DNV and agreed on new design principles. Key thing, bearing off the shelf, and that provides a little bit of air in the schedule. Really no air, but just to achieve the schedule. And it also reduces the design complexity overall. So not an in-depth calculation that I will explain, but the behavior of the cable in the carousel, and especially when on a moving ship during the operation, so not just transit, is pretty critical. And we went to the next step and we basically set up a model, a dynamic model, which actually simulates, ramps up the accelerations and shows the behavior of the cable in the basket. That made us more aware and then able to predict the behavior of the cable and the loading of the cable to the core and the walls, and to optimize the design further. So where we ended up is that DNV is fully aligned with what we're doing and thinking about adapting this method in the new rule sets or the updates of the rule sets, and basically raising the bar because there's a lot of unknowns like the shark in these carousel designs, and we try to make it more predictable and efficient. So what did the final solution offer? I think there's a few industry firsts in this. NC is now operating a concentric basket carousel, being 2 independent baskets, so they can be driven. For example, we have scrap cable on the inside, new cable on the outside. It can be DC cables, dual cores. There's a huge flexibility in the system. We're also able to remove the walls, and due to the whole drive setup being very accurate and controllable and predictable, we can synchronize the baskets. So that's a nice feature that actually works pretty well. And it's truly independent in that respect. And we see a benefit in the loading and the whole controllability. So the central drive hub with the bearings, like we set it up, offers flexibility. There's less parts, less failure modes, and above all, it's all concentrated in that middle part, which is good for maintenance. Predictable friction, which is way less than in the conventional systems, which provides accurate control. And there's a C-fastening arrangement. I didn't show it, but there's a UFO-shaped element in the middle, which can be welded independently of the equipment on deck. When the equipment comes with the shear leg, it means just dropped on top of that UFO and put into action. So what's up for the future? We see a lot of talks and clients that actually are asking about the DC bundles. We're also involved in delivering the biggest subsea trenchers. So that's future developments where we see a lot of demand for bundles. And bundles have their own challenges, let's say, handling different cables. It's just a big challenge for the burial, but also for the lay on the vessel, having different carousels that need to be synchronized. You actually want to have full control over the independent carousels and not snag cables during the lay process and reducing the lifetime. We're also working on a modular repair spread, pretty similar in terms of functionality as delivered, but to fit it on a smaller vessel. So there's more coming on that, but I cannot show the pictures yet. Technology challenges. The trencher you saw on the first slide actually goes to like 3.5 meters depth. Also there we're raising the bar, and the newest machines actually go beyond 5 meters. So that's already happening at the moment. We're now assembling the machines, 2 of them, which can go beyond the 5 meters. Pretty impressive. And another topic that we're working on is shared drive hub. So the principle we applied, which is proven now for like 4 or 5 projects. We also have an idea to use that in a flexible way to drive multiple carousels. And that principle, and in the conversation we have, this is an appealing thing because there's a lot of movements of cable around the world. And when you look at the different steps in the process, so being a manufacturer, producing the cable, transporting the cable to the actual offshore wind farm or the mobilization port, there's a lay contractor involved, and eventually there's a contractor that can do the repairs. They all need the carousel solutions, and what we propose is to have a modular system. So the dump steel, really, the baskets are configurable, and the key smart element of that is the drive system, which can be clicked under it, literally. So I'm pretty curious what your view is on this, if this is appealing and if you see benefits. We think it provides a nice solution. It's a reliable solution, and especially on the topic of circularity, it doesn't make sense to move a lot of steel over the world. There's a lot of waste of cost and energy involved. But again, it's the whole chain, the whole supply chain involved in the offshore wind industry that needs to make this happen. And especially the cable companies, and I'm looking sideways, are pretty interested in this because they fabricate the cable and need to move it around. And some of them are involved in the lay process and the repairs as well. So this is something we're exploring at the moment, and I'm keen to receive some feedback.
Okay. Do we have questions? I have one of my own. You mentioned the turntable capacity you've delivered to NC would be 400 tons, and you also mentioned you try to work out the specs of that system to match a big range of cable. I think of the Seawind vessel that was also on standby that had a 2,000-ton turntable. How did you arrive at 400 tons being sufficient? What's the sort of the goal you set there?
Yeah, it's not really up to us to decide on that, of course. It's the insight NC had on the repairs in the near future and beyond that, let's say. let's say the amount of spare cable that needs to be taken on board, but also certain specific lay projects for difficult conditions were part of that mix.
Yeah, okay. And then a follow-up question to that, the modular storage system you showed us, what would be the upper limit you see in terms of size of baskets you could handle? What's the weight? What's the volume?
In the meantime, so let's say that the past year, we also looked in parallel to different capacities. Roughly, you can say there's like 400 to 600 ton capacity. There's a step change to 1,500 tons. And then you straight away go to like 5,000 tons and 10,000 and beyond. We think, and that's based on the actual work we did on the designs, that there's a sweet spot around the 5,000 tons. And beyond that, the slew bearings get that big, and they're used in a segmented way in the big heavy lift cranes, but it doesn't match up in terms of cost anymore. So around 5,000 tons is the max we can do.
Okay, that's quite substantial.
It is,
Yeah.
and it comes with all the benefits.
Yeah. Okay. We have a question. Let's start. Oh, let's start here. Okay, you.
Jürgen, thanks. Just a question really about your work with DNV to reset the standard. Could you talk a little bit more about that and what has changed?
Up to now, I think nothing changed, but we had a different approach to the load share in the carousel. So the load actually, you can assume it's fully on the hub, you can assume it's on the walls, you can assume it's somewhere in between. And by actually modeling it in a proper way and discussing that from where we started actually with DNV, getting them involved, having open discussions, they can very much relate to what we did here. And the people involved have actually supported this and are looking to implement that, maybe incremental, I don't know, maybe in a big step change in the near future.
Okay, thanks. There's always that difference between a standard, which is lowest acceptable to certain players, and what insurers will accept. And we see that with degradation of allowances for friction, for instance, and then where you're applying the loading on the sidewalls. So I look forward to looking into that in more detail. Thank you.
What became apparent, I'm just coming into a new company for like 2.5 years now. In my previous company, we did a lot of cable there, and I was never allowed to touch cables because that was the UK. What I sense is that the cable equipment market is pretty small. It's pretty wild still. I think as the industry grows, we need to have a more common understanding of actual behavior of the cables in the equipment.
Thank you.
No.
Yeah, Jürgen, just a quick question. What's the typical cost of one of those systems, if you're able to say?
You mean the system I've just shown you?
Yeah, just the one there.
It ranges from like 2.5 to more million. Yeah.
Hi, Jürgen. Yes, thanks. Very nice equipment that you show there. You asked for some feedback, and I really like your modular approach for the storage facilities. Exactly. The only constraint that I can see is that the drive system, you cannot dimension it for the larger capacity carousels. So that would be a capex investment, because the same drive system is also should also drive the smaller carousels and the big ones. How do you see that?
Fair point. It is, you could just focus on what's in front of your feet and say, I need a 1,000 ton basket right now. You could also see it as an investment because you intend to use the equipment longer, for like maybe 5, 10, 15 years. So investing in a 5,000 ton hub and having a few projects where you drive a 1,000 ton basket, it's not a bad thing because you then have the equipment available to use on multiple projects. So I would say take the leap. I'm actually looking at that ourselves as well to see if we can make that investment. But that would be my answer. Yeah.
And being an equipment manufacturer myself, for all the downstream equipment, what comes after the carousel, there's of course a lot of synchronization necessary, to treat the cable in such a manner that it is not the integrity is not hurt. How do you see that? Because there's so many, like you also indicate, so many suppliers and different philosophies. How do you see that happening?
I think people need to experience that as well. I didn't mention the control system, but we also took the next leap, let's say, in terms of controls, integrating equipment, but also the interface to the operator, not being simple levers, but actually providing a decent SCADA system and integration. I think it's a matter of experiencing that and showcasing that it's actually working. Looking at the next projects where multiple cables are laid in bundles, I think the challenge is increasing, and you know that because you're delivering as well on these projects. It will be key, more important in the future to have full control, to just prevent damage from day one. Yeah.
Very well.
Yep. Do we have any more questions? No? Then, thank you very much.
Thank you.
All right, so we have arrived at the end of the conference, or at least of the presentation part of it. So I just want to take the last 1 or 2 minutes to thank all the speakers again for being here and presenting all these interesting topics to us. I also want to thank all the delegates who have indulged the speakers and let them speak about stuff that is exciting to only very few people on the planet. At least out of my experience, I do not get that opportunity very often, certainly not at home. So thank you for that. And also thank you to the organizers who made this event possible. Yeah, I hope that we will have more opportunities to meet up in this group. And the next one that is coming up, also organized by Lead Event, will be in London on the 18th and 19th of November. So if you enjoyed this, I'm pretty sure you'll enjoy the next iteration of the conference in London. Make sure to mark your agendas and yeah, book your spots. Thank you very much. And yeah. And let's take all the remaining discussions we might have left over lunch. So thank you.
Have a great lunch, and for all of you that go to the site visit, you can go to the registration desk and pick up the form of the site visit or visit your emails.